Hello, fellow Sapiens. Before we begin, take a breath, slow your thoughts. Whether you're lying awake, driving through the dark, cooking, or just trying to quiet your mind, this space is for that. A calm corner of the internet where we wander through science, history, and deep time, softly. Here at Sleepless Homo, we tell stories the slow way. No noise, no hype. Just humble researchers, old stones, quiet data, and the strange beauty of what we actually know so far. If you find comfort in that, in soft science and long thoughts, consider liking and subscribing. It helps other sleepless minds find this same stillness. Tell me where you listen. In bed, at work, through headphones in the dark, and if you drift off halfway through, there are timestamps waiting when you wake. And as always, stay curious, stay calm. Imagine the sky itself turning into a volcano. 74,000 years ago, on the island we now call Sumatra, the Earth drew a breath longer than any in recorded memory, and then exhaled a storm of fire that could be seen from space, if space had existed for anyone to see it from. The mountain was Toba, and when it spoke, continents listened. We have names for eruptions that scar a landscape: Krakatoa, Tambora, Pinatubo. But Toba was not an eruption. It was an event. A single convulsion that released enough energy to rewrite the planet's climate, carve out a lake large enough to be mistaken for an inland sea, and scatter ash halfway around the world. The mountain that would become Lake Toba had been restless for nearly 1 million years. Deep beneath its skin, magma accumulated in chambers tens of kilometers wide, buoyant and patient. With every pulse from Earth's mantle, new molten rock pressed upward, dissolving gases, thickening pressure, waiting. Magma is not a static pool. It's a living mixture of molten rock, crystals, and volatile compounds. When that mixture becomes saturated with gas, water vapour, carbon dioxide, sulfur dioxide, it transforms into a bomb whose casing is the Earth itself. At Toba, the casing failed spectacularly. When the pressure exceeded the weight of kilometres of overlying crust, the caldera's roof began to crack. Those fractures were the first warning signs, but in geological time they happened in an instant. The mountain's summit split open like a wound. Jets of superheated gas and magma blasted upward faster than sound. Within minutes, the column of ash and pumice rose more than 40 kilometres high, punching through the stratosphere. The eruption's column was so immense that it likely generated its own weather. Lightning storms born from the collision of ash particles, cyclonic winds circling the plume, darkness falling beneath it before the sun had even set. Scientists estimate the total volume of material ejected exceeded 2,000 cubic kilometres. To imagine that, picture every mountain range on an entire continent being ground into powder and thrown into the air. This was a volcanic explosivity index of 8, the highest rank our species has ever recorded. Each second, the eruption released energy equivalent to 1,000 Hiroshima bombs. And yet, all of it occurred in silence to anything living within its reach, because the shock waves would have killed hearing before the brain had time to register the sound. The molten heart of Toba did not simply vent, it collapsed. When that much magma escapes, the empty chamber can no longer support the crust above it. As the eruption continued, the roof caved in, forming a caldera roughly 100 kilometres long and 30 kilometres wide. Imagine a scar so vast it could swallow entire cities by the dozen. Today it holds Lake Toba, still steaming in places, still carrying the memory of that single exhalation. Around its edges, volcanic domes have arisen like the slow healing of a wound, each a reminder that the system remains alive, only sleeping. Ash began to fall across the Indian Ocean within hours. In some places the layer was centimetres thick, in others metres. Tephra, pulverised rock, glass and mineral fragments, drifted on high winds, settling over India, the Arabian Peninsula and East Africa. Grains from that eruption have been found in marine cores thousands of kilometres away. The finest particles, barely micrometers wide, remained aloft long enough to circle the globe multiple times before gravity pulled them down. Each one carried within it tiny bubbles of trapped gas, time capsules of what the atmosphere had been before everything changed. Those gases are what made Toba truly global. Sulfur dioxide rose into the stratosphere, and reacted with water vapour to form sulfuric acid aerosols, a thin reflective veil that dimmed sunlight. But that's a story for later. In this moment of eruption, the Earth's sky transformed into a glowing river of ash and lightning. For weeks, maybe months, the mountain expelled magma, pumice, and gas, in quantities almost beyond computation. The plumes spread in radial jets, feeding pyroclastic flows that raced across land at hundreds of kilometres per hour. These were avalanches of hot gas and shattered rock moving faster than any creature could flee, hotter than any fire could burn. The flows crossed valleys, lakes, and ridges as if they weren't there, filling them, erasing them. The sound waves from the blast likely circled the planet multiple times, as later eruptions like Krakatoa did. Atmospheric pressure waves recorded in modern times show how the air itself becomes an instrument, vibrating from the shock. In Toba's case, we have only models, but the magnitude suggests a planet that quite literally rang. Fine dust and gas injected into the stratosphere may have reached altitudes above 50 kilometres, a height where normal weather cannot wash it out. That isolation is what allows super-eruptions to change not just landscapes but global climate for years. The physical mechanics of Toba's eruption are still being modelled today. Volcanologists use a combination of field mapping, geochemistry and computer simulations to reconstruct its sequence. They study the crystal structures in pumice to estimate magma storage time, the orientation of ash grains to determine plume direction, and the isotopic composition of sulfur to gauge atmospheric reactions. Each piece of data is a whisper from 74 millennia ago, and like all whispers from the deep past, it comes with uncertainty. No direct witnesses survive to tell the story in words, only rocks, sediments, and chemistry. Lake Toba today is tranquil, a mirror stretching across the caldera floor. But that peace is deceptive. Beneath it lies the remnant magma system, slowly refilling. Seismic surveys show domes rising on the lake bed, the crust flexing as if breathing again. There will be eruptions in the future, smaller ones, perhaps large again. The timescale, though, is geological. Our species might not be here to see the next full exhalation, or we might have moved far enough to only read about it in the rocks of tomorrow. Scientists categorise Toba as a supervolcano, though that term is more poetic than technical. It describes any eruption ejecting more than 1,000 cubic kilometres of material, so rare that they occur perhaps once every 100,000 years. Earth has produced several such events. Yellowstone around 640,000 years ago, Taupo around 25,000 years ago, and Toba at 74,000. But none match Toba's known scale in the Quaternary period. It stands as the benchmark of what our planet can do when it reminds us who's in charge. At the eruption's heart, the magma was dacitic, rich in silica, viscous, prone to trapping gases. That chemistry explains the violence. More fluid magmas, like those in Hawaii, release gases gradually, producing fountains rather than detonations. Silica-rich magma acts like wet concrete filled with bubbles. The gas cannot escape until the pressure is catastrophic. When it finally breaks free, the magma fragments explosively, expanding its volume by thousands of times. Every ash particle from Toba began as part of a single continuous liquid mass that was ripped apart by expanding gas. In the first days, the eruption column may have collapsed repeatedly, sending pyroclastic flows tens of kilometres outward. Each collapse deposited ignimbrite, a welded layer of ash and pumice that still blankets Sumatra today. Geologists measure it in thicknesses of hundreds of metres. In cross-section, those deposits look like sedimentary pages in a book written by heat. Each layer tells of a pulse, a pause, another pulse. As the eruption waned, smaller vents may have opened along fractures around the caldera's rim, releasing final sighs of steam and gas before silence returned. The silence afterward would have been unlike anything alive today has experienced. No birds, no wind audible over the muffled landscape. The ash would absorb sound, dull light, and coat everything in fine grey powder. Even after rain began to fall, it would mix with the ash to form cement-like mud flows that hardened as they cooled. Rivers would clog, valleys fill, and coastlines shift. Satellite images of modern volcanic eruptions show plumes spreading like ink across water. Now imagine that multiplied by thousands. What remains astonishing is that the Earth, vast as it is carries the fingerprint of that single event in sediments everywhere. In Indian Ocean cores, a thin grey layer marks the moment. In African lake beds, microscopic shards of Toba glass lie hidden among diatoms and pollen grains. The same layer appears in the South China Sea and Arabian dunes, even in Antarctic ice. A planetary signature synchronized to one eruption. That is the reach of a mountain's breath. If we could stand there, 74,000 years ago, and watch from a safe distance, say, orbit, it would look like a scarlet bloom expanding over blue, a ring of incandescent clouds spiralling outward, lightning flickering through the ash, the plumes stretching past the horizon. The contrast between the serenity of distance and the violence below would be surreal. On the ground, there would be nothing to see but darkness and ashfall so thick that midday became night, and yet Toba was not unique in the history of the planet. It was part of a long geological conversation between pressure and release, creation and destruction. Volcanoes have always been agents of renewal as much as ruin. They build the crust that later holds forests, release gases that sustain atmospheres, and recycle the deep earth into surface life. Toba's eruption was catastrophic for the moment, but in the longer rhythm of geological time, it was one heartbeat in a restless world. We often think of mountains as permanent, but they are temporary wrinkles in a fluid planet. Toba reminds us that what seems immovable can melt in hours. The same crust that supports civilizations today is only a thin lid on a convecting interior. When that lid flexes, entire epochs can change course. The super-eruption 74,000 years ago did not just alter landscapes, it became a reference point in Earth's memory, a line in the stratigraphic record that future beings, if any, could read like a sentence beginning with, "Once there was fire." Even now, the aerosols from modern eruptions like Pinatubo in 1991 offer miniature versions of Toba's physics. They let scientists model how sunlight scatters, how sulfate particles grow, how winds distribute ash across hemispheres. By studying the small, we understand the enormous. Still, Toba remains a challenge, too large for full comprehension, too ancient for direct calibration. The only constants are the rocks, the chemistry, and the quiet inference that such power is still present beneath our feet. So what happens when a volcano big enough to dim the planet finally exhales? The answer is not drama, but mathematics. Gas pressure, magma viscosity, thermal energy, gravitational collapse. And behind all of that, the slow patience of geological time. The mountain does not intend destruction, it follows physics. And when physics aligns perfectly with pressure, the result is a story written in ash rather than ink, lasting longer than any civilization will. We can only guess what the first dawn after the eruption looked like, if the sun's disk appeared red through the haze, if the world smelled of sulphur and rain. In that silence, before humanity's struggles even began, the Earth reminded itself that renewal often begins with collapse. The rest of the story, the human part, comes later. For now, all we know is that once, 74,000 years ago, the planet spoke in fire, and everything listened. Imagine waking to a world where dawn simply doesn't arrive. Not just one morning of heavy clouds or volcanic twilight, but months of dimness where even midday carries the colour of dusk. 74,000 years ago, after Toba exhaled its ash and sulphur into the upper atmosphere, the planet began to forget the rhythm of its own light. It was not darkness in the way we know it, but a filtered world, bluish and grey, where sunlight scattered weakly through a chemical veil. The Earth had become its own shadow. Within days of the eruption, billions of tons of sulfur dioxide had risen high above the weather systems that usually clean the sky. At altitudes where raindrops cannot form, the gas reacted with water vapour to produce a delicate haze of sulfuric acid aerosols. Each droplet, only micrometers wide, acted like a tiny mirror, reflecting sunlight back into space. The result was a planetary dimming, a phenomenon scientists now call volcanic winter. It did not take a total eclipse to alter life's balance. Even a small fraction of sunlight blocked from the surface can cascade through the entire system of climate and ecology. Modern observations give us a sense of scale. When Mount Pinatubo erupted in 1991, its aerosols cooled the Earth by about 0.5 degrees Celsius for nearly 2 years. Toba's aerosol load was hundreds of times greater. Models suggest a global cooling between 3 and 5 degrees Celsius, with far deeper chills in the mid-latitudes and polar regions. Temperatures might have dropped 10 degrees in some areas, but more dramatic than the cold was the absence of light. Photosynthesis slowed, sea surfaces cooled unevenly, the ocean atmosphere engine that drives monsoons and trade winds began to falter. In equatorial regions, where warm seas usually give birth to predictable rain, the circulation patterns collapsed. The Indian monsoon, a heartbeat of planetary moisture, may have failed entirely for several years. Without that pulse, continental interiors dried out, forests thinned, and dust carried the taste of ash far beyond the eruption zone. The great rivers that rely on seasonal rains dwindled into sluggish veins of sediment. The planet was still breathing, but shallowly. The cooling was not uniform. Because the aerosols reflected sunlight rather than absorbing it, the stratosphere warmed even as the surface froze. That created a steep temperature gradient, altering jet streams and storm tracks. High-altitude winds shifted, trapping cold air over continents and redirecting moisture toward the oceans. Ice sheets at higher latitudes likely expanded rapidly, locking away fresh water and amplifying global albedo, the reflectivity of Earth's surface. More ice reflected more sunlight, deepening the chill. The feedback loop was mercilessly efficient. Even the chemistry of the atmosphere changed. The introduction of so much sulfur into the stratosphere reduced ozone concentrations, letting more ultraviolet radiation reach the surface when the haze finally began to thin. For a time, the planet traded visible light for invisible burn. It was a paradoxical kind of night, dim to the eye but harsh to the skin. The biosphere reeled from contrasts it had never encountered in such synchrony: darkness, cold, dryness, and chemical stress. From a geological point of view, these events are described in equations: aerosol optical depth, radiative forcing, global mean temperature anomaly. But behind each of those terms lies a world out of rhythm. Imagine tropical corals accustomed to narrow thermal limits suddenly plunged into water too cold to sustain them. Imagine tree lines retreating hundreds of kilometres within a single lifetime, glaciers reclaiming valleys, and rainforests collapsing into open savannas. Toba's cloud turned ecosystems inside out. The first months were chaos, the following years were silence. Dust settled slowly, not just from the volcano, but from the drying soils that could no longer bind themselves with vegetation. The planetary albedo increased further as pale dust and ash coated wide surfaces. Regions that had once absorbed sunlight now reflected it, extending the cool period long after the aerosols began to dissipate. Climate models suggest recovery might have taken a decade or more, but the memory of the event was etched into ocean circulation patterns for centuries. In polar ice cores, sulfate spikes mark the event like a scar. Layers of trapped air record a sudden drop in greenhouse gas concentrations, particularly methane, as wetlands froze and biological activity slowed. Oxygen isotope ratios show abrupt cooling. In marine sediments, shifts in plankton species reveal a brief but sharp interruption in productivity. Even without fossils of the moment itself, the planet's archives are unambiguous. Something enormous dimmed the sun. The strangest part is how quickly the system responded. Within a few weeks of the aerosol spreading, the global average amount of sunlight reaching the surface fell by as much as 20%. The planet cooled rapidly, not over centuries but in seasons. To climate scientists, this speed is what defines a super-eruption's true violence. Not the explosion itself, but the suddenness with which it forces the entire climate engine into a new state. For Earth's biosphere, accustomed to gradual change, the shock must have been absolute. In this suspended light, photosynthesis faltered. Phytoplankton, the microscopic algae that form the base of the marine food web, depend on sunlight penetrating the upper ocean layers. With light levels reduced, their growth slowed dramatically. This altered the global carbon cycle. Less photosynthesis meant less carbon dioxide drawn from the atmosphere, temporarily buffering further cooling but also delaying recovery. It was as if the planet had pulled a blanket of ash over itself and decided to rest. The hydrological cycle weakened too. Cooler oceans evaporate less moisture, which means fewer clouds and less rain. The paradox is that the same eruption that darkened the sky also dried the land. Deserts expanded, Even regions far from Toba experienced shifts toward aridity. Lake levels dropped. Dust from newly exposed soils entered the atmosphere, creating secondary feedbacks that further scattered light. In a sense, the eruption had seeded the sky twice, once with its own ash and again with the planet's dust. In higher latitudes, snowfall increased despite the overall dryness, because colder air can hold less moisture but releases it more readily as snow when it does rise. The growing snowfields and ice caps reflected even more sunlight, locking the planet into a longer cool phase. Some climatologists have proposed that Toba's eruption may have accelerated glaciation in the northern hemisphere, nudging Earth into the deeper chill of the last ice age. The timing is close, though cause and effect remain uncertain. As always, the record speaks softly, and we can only listen. Chemical reactions within the stratosphere gave the sky a strange hue. Volcanic aerosols scatter blue light more efficiently than red, so twilight would have been vivid. Sunsets long and copper-coloured, stars muted behind an ever-present haze. At night, the moon would shine dimly through a veil, its brightness diffused. Even lightning took on a different colour, refracted through fine acid mists. From the ground, the heavens might have looked almost painted, beautiful in a detached and toxic way. From a purely physical perspective, Toba transformed the balance between incoming and outgoing energy. Before the eruption, Earth's energy budget was roughly equal. Sunlight absorbed was re-radiated as heat. Afterward, more energy was reflected than absorbed. The deficit cooled the surface and oceans, setting off chain reactions that even today are hard to fully simulate. Climate systems are non-linear. Small changes can trigger outsized responses. Toba's cooling was not merely proportional to its sulfur output. It was amplified by the complexity of feedbacks connecting atmosphere, ocean, ice, and land. The first rains that followed would have been acidic. The sulfuric particles eventually descended into the lower atmosphere. They mixed with water to form dilute acid rain, corroding leaves and leaching nutrients from soil. In lakes and rivers, acidity temporarily altered chemistry, affecting the balance of dissolved minerals. Yet even as this happened, the aerosols continued to reflect sunlight from above, creating a two-tiered world, corrosive below, reflective above. Over the next few years, the stratospheric veil slowly settled. Gravity and precipitation washed particles out of the sky, layer by layer. But the climate inertia ensured that cold persisted long after clarity returned. Oceans had cooled deeply, and their slow mixing times, centuries in some cases, meant recovery would be delayed. The surface eventually brightened again, but the memory of reduced heat flux lingered like a phantom. When modern researchers reconstruct this period, they rely on a patchwork of proxies: ice cores, marine sediments, cave formations, even tiny air bubbles trapped in volcanic glass. These fragments tell the story of a planet that, for perhaps 2 years, lived under a diffuse half-light. For comparison, the smallest volcanic winters in recorded history have disrupted agriculture and altered weather worldwide. Toba's scale was orders of magnitude greater, and yet the world did not freeze solid. Oceans retained enough heat to buffer the extremes, and the sun, though muted, never vanished completely. In that delicate balance lay the seed of recovery. The lesson is that Earth's climate is both fragile and resilient. Fragile because a single event can tip it into temporary chaos. Resilient because the same physics that drives catastrophe also steers the return to equilibrium. Over time, aerosols settle, albedo shifts back, and the solar constant reasserts itself. The planet remembers how to be warm. But the silence left behind by such darkness cannot be measured in degrees. It is a geological quiet, a pause between pulses of light. For nearly 2 years after Toba's eruption, the Earth existed in that twilight, neither night nor day. The biosphere slowed but did not die. Winds weakened, rains faltered, temperatures dropped, but the great cycles, carbon, water, heat, continued their work beneath the dim sky. Eventually the haze thinned. The sun returned not as a sudden sunrise but as a gradual easing of grey into gold. In that slow brightening, the planet began to remember itself. And yet one question remains, more poetic than scientific. When the world goes dark for that long, does life remember what light means, or does it have to learn it again? Imagine paradise beneath a blanket of ash. Not fire or chaos anymore, but stillness, a soft grey snow that never melts. 74,000 years ago, in the first weeks after Toba erupted, the tropical world fell silent under layers of fine volcanic dust. Where rainforests once glistened, everything dulled to the same colour. Green became grey, rivers turned into slow channels of silt, and the air smelled faintly of stone. The eruption's fury had already subsided. What followed was quieter, slower, and far more enduring. The fall of ash upon what had once been Eden. The Toba plume had reached higher than any mountain, and when gravity finally claimed it, the sky began to snow glass. Microscopic shards of volcanic silica drifted downward, carried by shifting winds across the Indian Ocean basin. Each grain was lighter than sand, but sharp enough to scour leaf surfaces and clog pores. When they landed, they formed a dry abrasive sheet, 5 centimetres thick in some regions, half a metre in others. For the people and animals not yet part of this story, it would have looked deceptively peaceful, a silent storm settling over half a continent. From Sumatra, the heaviest ash fell within hundreds of kilometres, burying forests outright. Pumice fragments rained into rivers, turning them opaque. Ash-rich mudflows called lahars thundered down slopes, destroying everything in their path and then hardening like cement. In what is now northern Sumatra, layers of ignimbrite still measure tens of metres thick, a rock record of that smothered world. Farther away, across the Indian Ocean, the ash thinned to millimetres, but its chemical influence persisted for centuries. To the northwest, the Indian subcontinent lay directly downwind. Winds from the equator carried fine ash particles across the Bay of Bengal, blanketing what are now Andhra Pradesh, Tamil Nadu, and beyond. Archaeological sites such as Jwalapuram preserve this layer in remarkable detail. Fine grey silt sandwiched between older and younger soils. Beneath it lies a world of stone tools and river pebbles. Above it, silence. That thin boundary is both geological and ecological, before Toba and after Toba. The land that had been lush and monsoonal became barren almost overnight. The ash fallout blocked sunlight from reaching leaves, halting photosynthesis. The chemical nature of the tephra, rich in sulphur and metal oxides, acidified surface water and leached nutrients from soil. Roots suffocated under the compacted dust which sealed the ground against air and moisture. Within weeks, forests browned, then blackened, then collapsed into layers of decomposing debris trapped beneath the grey crust. Seeds sprouted weakly, unable to pierce the surface. It was a biological reset button pressed by the sky. The Indian Ocean itself bore the scars. Floating mats of pumice drifted for years, colonised eventually by algae and barnacles, but at first sterile, reflecting sunlight back to space. Ash falling into the ocean altered its chemistry, particularly the delicate balance of silica and iron that supports plankton growth. Core samples show abrupt changes in diatom species and productivity. The sea surface turned more reflective, the same feedback that cooled the planet on land continuing over water. In Southeast Asia, where dense rainforests had dominated for millions of years, the canopy collapsed under the weight of ash. Leaves that once captured sunlight and rain now trapped abrasive dust, tearing under their own weight. Tree ferns, palms, and dipterocarps, all sensitive to drought and acidity, struggled. Streams that once ran clear carried grey slurry. The ash clogged their beds, forming unstable floodplains that shifted with every rainfall. When the first monsoons returned months later, they washed the ash downstream in enormous pulses, choking deltas and mangroves. The recovery of those systems would take centuries. To the southwest, over the Arabian Sea and into eastern Africa, the ash layer thinned but did not disappear. Even there, microtephra, particles invisible to the naked eye, landed on savannas and wetlands. In East Africa, these grains would later be identified within lake sediments, confirming the reach of Toba's breath. The distance was staggering, more than 7,000 kilometres from the eruption's centre. This was a global dusting, delicate yet deadly altering surface albedo and nutrient cycles across continents. Ash interacts with the world in curious ways. It is both sterile and fertile, killing plants at first, then feeding them much later. In the short term, its glassy particles cut leaves and clog stomata, blocking respiration. But over time, as water weathers it, volcanic ash releases potassium, calcium, and trace minerals that eventually enrich new soils. In that sense, the destruction it caused was temporary, yet the immediate aftermath was nothing less than ecological collapse. In tropical regions where biodiversity once thrived, the sound of insects vanished, replaced by the soft hiss of falling dust. Scientists studying ancient lake sediments in India and Malaysia find clear signatures of this silence. Pollen counts drop dramatically within the ash horizon, replaced by layers dominated by spores of ferns, plants that specialize in recolonizing disturbed ground. This suggests large-scale forest die-offs followed by slow ecological succession, a rebuilding of life from spores upward. In geological terms, it happened quickly. In biological terms, it was an age. Rainfall patterns changed too. Ash particles seeded clouds but also disrupted convection, producing uneven, short-lived downpours. When the rain finally came, it mixed with acidic aerosols still descending from the upper atmosphere, forming a corrosive drizzle that stripped bark and etched rock. Rivers swelled with grey water, carrying fine sediments far out to sea. Delta systems expanded temporarily as they filled with ash-laden deposits, later to be eroded again when normal flow resumed. Each process left its own line in the rock record, a chaotic chapter written in mud. One of the enduring mysteries is how life at the edges of the fallout zone responded. In parts of India and Southeast Asia, evidence suggests that some vegetation recovered surprisingly fast once the ash was stabilised by rain. Pioneer species, grasses, shrubs, opportunistic trees, began to sprout within years, exploiting the newly opened sunlight once the haze began to clear. In other regions, recovery took far longer, limited by nutrient loss and ongoing cooling. The variability reminds us that even a catastrophe of this scale did not act uniformly. The planet's diversity of climates created a patchwork of outcomes, deserts forming in one place, new wetlands in another. The rivers told the story in slow motion. Ash settled first as a fine suspension, then as dense layers that altered the course of flow. Channels clogged, forcing water to carve new paths. Old floodplains turned into stagnant lakes, anaerobic and dark. These transient water bodies became traps for organic material and new microenvironments for the few species that could endure. In those still pools, the chemical composition of water changed dramatically. More silica, more sulfur, less oxygen. The echoes of those conditions are preserved today in mineral nodules and sediment laminations. Further west, across the Indian Ocean, fine ash continued its quiet fall upon the coastlines of Africa. There, it mixed with pre-existing soils and left only a faint trace, detectable today through geochemical analysis rather than visible layering. Yet even that thin dusting may have altered plant growth and water chemistry. Ash-laden winds reaching the equatorial belt could have slightly cooled regional sea surface temperatures, influencing rainfall patterns for years. Every flake mattered. Every grain of glass changed how sunlight touched the surface. From the standpoint of geology, the ash distribution map is breathtaking in its symmetry. Using chemical fingerprints, ratios of elements like zirconium, titanium, and iron, scientists can trace single grains back to their volcanic source. Each discovery of Toba glass in distant cores is a reminder of how connected the planet is, how one explosion on a single island could touch everything from the Arabian deserts to the African highlands. The ash was global graffiti, marking time in a language of chemistry and wind. In Malaysia, ash deposits found within cave systems record a unique microclimate story. Stalactites grew differently during this interval, their layers thin and dull, indicating lower water flow and reduced vegetation above ground. Even underground, the darkness above had consequences. The biosphere's pulse slowed from the canopy to the caves, and yet, out of this ashfall, the stage for renewal was quietly being set. Volcanic glass, though deadly at first, breaks down into some of the richest soils on Earth. Regions like Java, Bali, and Sumatra today owe their fertility to this ancient catastrophe. When life returned, it returned to a world primed for abundance. The very dust that once smothered paradise would later feed it. This paradox, destruction that leads to renewal, is one of the constants of geological time. Every layer of ash carries the potential for both silence and rebirth. The forests that vanished after Toba's eruption were not lost forever. They simply went underground, into seeds and spores waiting for the sky to clear. When sunlight finally returned years later, photosynthesis resumed as if the planet had been holding its breath. The landscapes shaped by this ashfall were unrecognisable for centuries. Valleys filled, coastlines moved, ecosystems reinvented themselves. The world had not ended. It had been remade. What we call catastrophe was, to the Earth, merely another experiment in change. So what does paradise look like under 5 centimetres of ash? It looks like the beginning of something else, a blank canvas drawn by the hand of geology, waiting for life to remember its colours. Imagine a world where every horizon is grey, and yet, somewhere within that silence, a small fire still burns. 73,800 years ago, when the Toba eruption had dimmed the skies and the forest had turned to ash, there were still embers glowing somewhere on Earth. Not many, just enough to keep light alive against the grey. Somewhere along the southern coasts of Africa, within caves that opened toward a dim ocean, small groups of early humans sheltered near flickering hearths, using the last warmth of the planet's breath to endure a world that had gone cold. In the record of stone and soil, their presence is barely more than a whisper. Thin bands of charcoal layered between ancient sands, shell fragments blackened by heat, traces of soot on the roofs of caves long sealed by time. But these faint marks tell a story of persistence. While much of the planet struggled beneath volcanic haze and dying vegetation, a few regions managed to sustain enough stability for life to continue. Scientists call these places refugia, pockets where climate and geography combine to protect ecosystems from the worst of the planetary chill. One of the most significant of these refuges lies at the tip of Africa, along what is now the southern coastline, stretching from the Cape to the Indian Ocean. Cool ocean currents met warmer land air, creating local weather patterns that defied the global freeze. The Benguela upwelling brought nutrient-rich waters to the shore, feeding marine life even when inland vegetation collapsed. The result was an unusual stability. While forests died, the ocean continued to offer food. Mussels, fish, and seabirds persisted. In sites such as Pinnacle Point and Clayse's river mouth, layers of ash and sediment show that humans had already learned to harvest this coastal abundance long before Toba's eruption, and when the eruption came, these shores remained among the few places where survival was possible. The geological clues are subtle. Ash from the eruption travelled as far as southern Africa, but its deposits there are thin, mere traces mixed into older sands. Yet within those layers, archaeologists have found evidence of continuous fire use, burned shell fragments, heat-altered stones, charcoal horizons uninterrupted by long gaps. That continuity suggests that the people living along these coasts did not vanish during the global dimming. They endured even as inland ecosystems faltered. The key to their endurance was not technology in any modern sense, but geography. Coastal environments offered predictability when everything else failed. Tidal rhythms continued regardless of sky colour. Marine resources, unlike forest fruit or inland prey, were less dependent on rainfall or vegetation. Even as the air cooled and the land dried, the ocean remained alive. The shell middens, ancient heaps of discarded shells and bones, became the geological fingerprints of survival. In their silence, they speak of countless small meals, of hands cracking shells beside fires, of continuity measured not in abundance but in persistence. Further north, along parts of East Africa and possibly Arabia, similar microclimates may have provided refuge. Where the monsoon failed, small wetlands and coastal lagoons might have remained, fed by groundwater or localised rainfall. These were temporary havens, narrow windows of habitability in a world sliding toward desolation. But for early humans, they were enough. Even a small patch of stability could sustain a group long enough for the skies to clear. On the other side of the Indian Ocean, closer to the eruption's heart, survival seems less likely but not impossible. In the Indonesian archipelago, where ashfall was heaviest, evidence of continued ecosystems has been found in volcanic soils that began to recover surprisingly fast. Lava domes cooled, rain returned, and within decades pioneer plants began to grow over the grey crust. Charcoal fragments within these layers suggest that fire returned almost as soon as vegetation did, whether ignited by lightning, by volcanic heat, or by the deliberate hands of survivors, we cannot say. fire itself became both a tool and a symbol of resilience. It was not just warmth, but continuity, a visible defiance against the suffocating grey. In conditions where sunlight dimmed and night stretched cold, the mastery of flame meant the difference between extinction and endurance. Maintaining fire required more than ignition. It demanded care, protection from wind and damp, and the knowledge of which materials would still burn in a world drenched by acid rain and ash. Charcoal records preserved in caves along Africa's southern coast tell of fires relit again and again across centuries. Each layer of burned residue is a note in the long song of human persistence. It is remarkable that even during periods of environmental collapse, traces of controlled burning appear consistently in sediment cores. Charcoal abundance does not vanish. It fluctuates but remains detectable. This suggests that localized ecosystems, perhaps patchy grasslands or surviving thickets, still supported enough plant material for natural and human-made fires alike. Even when vast regions turned barren, small refuges remained green enough to smoulder. Coastal refugia were not the only safe zones. Some inland regions, buffered by unique topography or hydrology, may have provided similar sanctuaries. In the Ethiopian highlands, for instance, caves and valleys near ancient lakes might have maintained milder temperatures due to altitude and water regulation. Evidence from lacustrine deposits shows that even during periods of global cooling, some freshwater ecosystems persisted. Life contracts in hard times, but it rarely disappears altogether. It hides, adapts, and waits. The persistence of foraging groups in these environments depended on more than food. It required ecological intelligence, a deep familiarity with patterns in weather, tide, and terrain. To endure, early humans would have had to move carefully between resources, timing their activities to seasonal changes even when seasons themselves became unpredictable. Their existence was a kind of dance with the collapsing climate, each decision guided by ancestral memory and observation rather than by chance. From a scientific perspective, we can trace this endurance through environmental proxies rather than bones. Charcoal particles in lake cores align with stable isotope signals suggesting periodic vegetation recovery. Shell middens correspond to intervals of stable sea levels and moderate temperatures. Even the presence of marine calcium in sediments far inland hints at the trade of shells or the migration of coastal peoples. It is through these indirect clues that we glimpse the flicker of survival, the few fires that stayed lit, not as metaphor but as data. When scientists reconstruct the post-Toba landscape, they see a mosaic rather than a wasteland. Some areas were indeed devastated beyond repair, but others acted as cradles of resilience. Southern Africa's coasts, parts of East Africa, and perhaps isolated regions of Indonesia formed a network of survival zones that allowed life, and the human lineage, to persist. The distribution of later archaeological sites corresponds eerily well to these predicted refugia, as if the map of endurance was already drawn by climate long before we could read it. The beauty of this story lies not in heroism, but in continuity. These were not conquering survivors, but caretakers of embers. Their fires burned low, sheltered from the wind, just enough to cook, to warm, to signal life against a dim horizon. Over generations they carried that light through centuries of cooling and change, until the planet remembered how to be bright again. Every later hearth, every controlled flame, carries a trace of those first lights that never went out. In the archaeological record, we can measure catastrophe in ash layers, but we measure resilience in charcoal. Each fragment, no larger than a fingernail, contains within its carbon structure the fingerprint of an ancient fire. Some are from wildfires sparked by lightning, others from deliberate hearths built by human hands. Together they tell the same story, that even when the sky turned grey, something kept burning. There is humility in that realization. We often imagine survival as conquest, as adaptation through brilliance or luck. But here, in the aftermath of Toba, survival meant something quieter. Patience, endurance, the simple act of keeping a flame alive long enough for the next sunrise to return. The people of that dim age did not rebuild the world. They outlasted it. And so, when we think of the global catastrophe 73,000 years ago, perhaps we should not picture chaos or despair. We should picture small fires along distant coasts, flickering behind stones, their smoke rising weakly through the cold air. The light of those fires was dim, but it was enough. It was the soundless heartbeat of a species waiting for the earth to thaw. Who kept the flame alive when the air itself turned grey? We cannot name them, nor see their faces, but the smoke that once rose from their fires has long since joined the air we breathe. The memory of their endurance is still here, carried invisibly within the planet's chemistry and within us, the distant glow of those few fires that never went out. Imagine a world where every ancestor you've ever had could fit inside a single small valley. 73,000 years ago, the Earth had quieted after the eruption, but the silence hid something deeper, a genetic whisper suggesting that nearly all of humanity had been reduced to a few thousand surviving individuals. Whether that number was truly so small remains uncertain, but the evidence carried in our DNA hints that the story of who we became may have begun not in triumph, but in scarcity. The idea is simple and haunting at once. Did we almost vanish, or did we just hide long enough to change? When scientists began comparing human genomes in the late 20th century, they found a striking pattern. Across populations scattered over continents, our genetic diversity was surprisingly low. The difference between any two modern humans is far smaller than that between two chimpanzees from neighbouring forests. This uniformity puzzled researchers. It suggested that, at some point, our ancestors had passed through a severe population bottleneck, an event in which numbers collapsed so dramatically that only a few lineages survived to repopulate the world. In genetics, that kind of narrowing leaves a signature: reduced variation in both mitochondrial DNA, which passes through mothers, and nuclear DNA, which is inherited from both parents. Early calculations using mitochondrial data proposed an especially grim picture. Based on mutation rates, researchers estimated that as few as several thousand reproductive adults might have lived through this period, perhaps even fewer. The timing coincided roughly with the Toba eruption, leading to a hypothesis that the volcanic winter had nearly erased us. It was a compelling narrative: the supervolcano as near-extinction trigger, the grey skies as crucible for modern humanity. But science, as always, resists simplicity. As genetic data expanded, the picture began to blur. Mitochondrial DNA tells only one side of the story. Because it follows maternal inheritance, it represents a single genealogical thread. Nuclear DNA, by contrast, mixes countless threads. When scientists began sequencing entire genomes, they found evidence for more complex demographic patterns. Some models still supported a dramatic bottleneck around 70 to 75,000 years ago, while others showed a more gradual reduction, stretched over tens of thousands of years. The sharp cliff of extinction softened into a landscape of population contractions, local recoveries, and slow mergers. In southern Africa, where archaeological evidence suggests continuity through the volcanic period, genetic diversity remains high even today. That region may have served as a reservoir for human variation, a place where population sizes stayed relatively large despite global cooling. East Africa tells a different story: smaller, more fragmented groups, consistent with climatic stress. It is as if the human species became a patchwork quilt of refugia, some shrinking, others holding steady, all connected by thin threads of migration and intermarriage within the continent. The bottleneck, then, may not have been a single doorway we barely slipped through, but a corridor filled with branching paths. Modern estimates of the effective population size, the number of individuals actively contributing to the gene pool, suggest that during this period it may have fallen to somewhere between a few thousand and perhaps 20,000. That is not extinction, but it is perilously close to the limits of long-term genetic stability. When populations remain small for extended periods, rare mutations can dominate by chance, and harmful traits can spread. Yet paradoxically, small populations also accelerate change. In such intimate scales, innovations, behaviours, and even beneficial genetic variations can move swiftly through groups. A species under pressure becomes a species under transformation. What we know from paleoclimate data supports the notion of fragmented survival. Between 73 and 70,000 years ago, Africa was not a single landscape but a shifting patchwork of arid zones, lakes and coastlines. Glacial cycles had drawn water northward and deserts expanded. Central Africa's rainforest retreated into smaller pockets, isolating populations much like islands. To the south, coastal refuges provided relative stability. These ecological islands may have fostered genetic islands too, small, partially isolated groups that occasionally reconnected when conditions improved. The question then is not whether we almost vanished, but whether our scattered ancestors were ever truly apart. The genetic data reveals deep structure within Africa at this time, multiple regional lineages that persisted separately for tens of thousands of years before blending back together. Some researchers call this a braided stream model of human evolution, a metaphor drawn from rivers that divide and rejoin. Under this view, the bottleneck was not a single narrow gate, but a set of intertwined channels that occasionally ran thin and dry, yet never ceased flowing entirely. Mitochondrial lineages known today as L0, L1, and L2 trace their origins to this era. They branch from ancestors who lived in different regions of Africa, suggesting that no single group held the entirety of human continuity. The merging of these lines later would form the genetic foundation of all present-day humans. That means that even amid near-catastrophic environmental pressure, our species remained geographically and genetically plural, a chorus of small voices surviving in scattered shelters. Another clue comes from nuclear DNA patterns that record changes in population size over time. These data indicate that although diversity decreased, it never reached the vanishing point. There was compression, but not collapse. Some scientists argue that what looks like a bottleneck might actually be the legacy of long-term population structure, a byproduct of small, semi-isolated groups rather than a sudden die-off. If that is true, then Toba was less a bottleneck and more a backdrop, a natural disaster that intensified pre-existing trends rather than rewriting them. Still, the coincidence of timing remains hard to ignore. Climate records from marine sediments and lake cores show sharp cooling and aridity following the eruption, conditions that could easily have reduced habitable zones. Even if the bottleneck began before Toba, the eruption may have deepened it, cutting already sparse populations into smaller enclaves. Within these enclaves, culture, communication, and genetic inheritance all became tightly woven. 1,000 years of isolation could reshape not only who survived, but how they lived. There is humility in how scientists frame these findings. Every genome sequence, every fossil, every sediment core offers another piece of a puzzle that no one will ever see complete. Models differ not because one is right and another wrong, but because the truth lies somewhere between them, in the gradients of probability and the unknown biases of ancient survival. The human past is not a straight line, but a foggy coastline, full of peninsulas and coves that appear and disappear with the tides of discovery. From that fog, one message emerges clearly. The population that carried us through this period was small enough for its genetic echo to be heard in all of us today. Whether the number was 5,000 or 50,000 hardly matters. It was limited, fragile, and enough. From such scarcity arose the species capable of crossing oceans and building civilizations. The resilience encoded in our DNA is not a story of dominance, but of endurance through constraint. Some researchers view this interval as a turning point in our biological and cognitive development, not because mutations magically appeared during the volcanic winter, but because demographic stress amplifies selection. In small, isolated populations, behaviours that promote cooperation and adaptability gain value. Groups that shared food, maintained social bonds, and transferred knowledge would have had higher chances of survival. Over generations, those habits became intrinsic to our species' success. If so, the bottleneck was also a bridge, an evolutionary filter that refined the traits most compatible with survival in uncertainty. Yet it is important to resist the temptation of destiny. The evidence does not show that we were destined to succeed because of catastrophe, only that catastrophe shaped the pathways available to us. The same pressures could have erased us entirely. The line between extinction and endurance is thinner than science can measure. Our genetic uniformity today is both a mark of survival and a reminder of how close that balance may have been. As we piece together the story of this dim epoch, the question remains open. Did humanity almost vanish, leaving only a handful of lineages to repopulate the Earth? Or were we simply hidden from view, divided into many small groups that persisted quietly until the world grew gentle again? The evidence leans toward a mixture of both, a contraction that pruned the tree but did not uproot it, The branches that survived spread and merged until diversity blossomed once more. What matters most is that the record of that narrowing remains written in us. Every human alive today carries genetic threads that trace back to that period of scarcity. Our shared ancestry is not a symbol of superiority or progress, but of how fragile continuity can be. We are, in a sense, the descendants of those who hid well, who endured long enough for the sky to clear. So when we speak of bottlenecks, perhaps we should also speak of bridges. Each narrowing in history leads not only to loss but to new possibility. The Toba period, whether catastrophic or survivable, marked one of those crossings. Through ash, cold and near silence, a few small populations carried forward the memory of life. From them came us. Imagine the tide pulling back and revealing a world that never truly froze. 72,000 years ago, when much of the interior of Africa was locked in drought and chill, the southern coastlines remained alive. Each ebb of water uncovered a banquet laid out by the ocean. Shellfish clinging to rocks, seaweed streaming in shallow pools, crabs hiding beneath stone. It was a landscape that reset itself twice a day. For a species that had learned patience, predictability was survival. When the rains failed and the forests thinned, the tides kept coming. Along the southern rim of Africa, a few refuges offered what the rest of the continent could not: stability. The caves at Pinnacle Point, 𝐓𝐈𝐌𝐿𝐄𝐒𝐓𝐀𝐌𝐏𝐒 and Blombos opened toward a sea that pulsed with regular rhythm while the world behind them grew erratic. Upwellings from the Benguela and Agulhas currents brought cold, nutrient-rich waters to the surface, fueling plankton blooms that fed fish, seals and seabirds. Mussel beds regenerated with every cycle of the moon. Even in years when inland plants withered, the coastline shimmered with life. To understand why these places mattered, scientists look first at their geology. The continental shelf off southern Africa is broad and shallow. During cooler phases, sea levels dropped, exposing tidal flats that stretched far from the present shore. These new landscapes were temporary but abundant, thick with mollusks, urchins and edible seaweeds. When the sea rose again, the same regions replenished. For coastal foragers, the edge of the continent was not a boundary, it was a conveyor belt of food. At Pinnacle Point, excavations have revealed dense layers of shells and marine sediments dating from around 72 to 70,000 years ago. These middens, ancient heaps of discarded shells, mark some of the earliest known evidence of sustained coastal subsistence. Their composition tells a detailed ecological story. Limpets dominate the deposits, followed by periwinkles, mussels and barnacles, all species that live in predictable zones of the intertidal range. Their size distribution suggests repeated harvesting, careful enough to let populations recover. It was not random scavenging, but a rhythm of gathering refined through generations. In the same layers, marine sediments contain micro-remains of seaweed and other coastal plants. Seaweeds rich in iodine, carbohydrates and trace minerals could be dried and stored, forming an overlooked but critical dietary resource. Unlike meat or fruit, they were reliable in every season. The ocean's constancy offered what the changing land could not: a baseline of nourishment. Stable isotope analyses of ancient shells provide a record of the environment itself. Ratios of oxygen isotopes reflect sea surface temperatures, showing that the waters near the southern tip of Africa remained relatively cool but stable during the climatic chaos following Toba. This stability may have buffered the region from the severe droughts that afflicted the interior. Where monsoons failed, coastal fog and marine moisture kept vegetation along the cliffs and dunes alive. The coast was not lush, but it was steady. Archaeologists studying 𝐓𝐈𝐿𝐄𝐒𝐓𝐀𝐌𝐏𝐒 find similar evidence. Layers of shells alternate with traces of hearths and animal bones from seals and seabirds. Here, early humans exploited both marine and terrestrial foods, moving between the beach and nearby river valleys. The faunal record shows a preference for medium-sized prey, species that could be caught without organised hunts. It paints a picture of small mobile groups that stayed close to the shoreline, returning to familiar spots with the tides. This reliance on coastal resources was not a step backward, but an adaptation to a world in flux. Inland, ecosystems were collapsing under cooling and aridity, and many animals migrated or died out. On the coasts, the ocean's upwelling systems continued to function, creating microclimates of abundance. The rhythm of the tide replaced the rhythm of the seasons. To live by the sea was to step into a more predictable world. Geochemical evidence supports this view. Marine calcium and strontium isotopes preserved in shell middens correspond with modern intertidal chemistry, confirming that these foragers harvested during times of ecological continuity. The presence of multiple species with differing habitat depth suggests flexible foraging during low tide, people wading, prying, and scraping along rocks. Every motion implied observation and memory, knowing which pools refilled, which reefs yielded best after storms, which months brought the fattest mussels. Knowledge was the tool that mattered most. For scientists, these coastal refuges illustrate how environmental diversity can act as a life raft for species under stress. They show that survival sometimes favours the margins rather than the centres. When vast savannas turned to dust, narrow belts of shoreline kept life's rhythm intact. These edges, overlooked in grand narratives, became the quiet theatres of continuity. The archaeological traces are humble yet profound. Burnt shell fragments testify to simple cooking methods, placing shellfish directly in embers or on heated stones. Some shells show discoloration consistent with boiling, implying that people may have used perishable containers made of skin or plant material. Around these hearths, sand is darkened with charcoal, and layers of ash form thin horizons, each one representing another generation that managed to make it through another cold year. Coastal subsistence also offered resilience through diversity. A single foraging group could exploit dozens of species: fish trapped in tidal pools, seabird eggs, marine snails, seaweeds, and small mammals from nearby dunes. Such variety reduces the risk of collapse. When one source failed, another could be substituted. The ocean provided a living safety net woven from salt and thyme. Even the landscape itself helped. Caves along the coast provided natural shelter, protecting fires from wind and preserving warmth against the cold air carried inland from the glacial south. These shelters, layered with smoke and shell, became both homes and archives. Within their sediments, scientists now find the chemical ghosts of those fires, microscopic flecks of carbon that survived 70 millennia. When analysed, they reveal the composition of wood and fuel, showing that coastal shrubs and seaweed were burned together. The ocean not only fed, it warmed. What makes these coastal refuges so significant is that they appear continuous through climatic fluctuations. Where other regions show breaks in occupation or ecological collapse, the coastal sites remain steady. It is as if the shoreline acted as a biological metronome, setting the tempo for human endurance. Each generation learned the same tides, the same patterns of shell growth and wave rhythm. The sea was both teacher and constant. From an ecological perspective, these refuges also sustained biodiversity beyond humans. Coastal dunes and lagoons served as sanctuaries for birds, reptiles, and small mammals displaced from the arid interior. Mangroves and salt marshes trapped nutrients washed down from inland, creating miniature ecosystems that defied the global cooling trend. In this way, the coastlines were not just human havens, they were nodes of resilience in the planet's broader web of life. By studying isotopic signatures in ancient shells and animal bones, researchers can even reconstruct the seasons in which people harvested. Many shells show growth rings corresponding to cool water months, suggesting that groups timed their gathering to maximize yields while avoiding storms. This pattern hints at long-term familiarity, even planning. Yet what makes it remarkable is its simplicity. The entire strategy relied on one thing that the rest of the world had lost: predictability. The same predictability shaped social stability. A dependable food source allows for smaller territories, reduced conflict, and the time to pass knowledge across generations. The coastal refuges thus did more than feed. They created continuity, an unbroken line of survival across centuries of climatic instability. When later populations spread again into the continent's interior, they may have carried with them the memory of these tides, the unspoken understanding that security can be found where land and sea meet. Modern climate models confirm how rare such zones would have been during the late Pleistocene. Simulations show vast areas of central and northern Africa under extreme aridity, while narrow belts along the southern and eastern coasts remained humid. These belts coincide almost perfectly with known archaeological sites from the period. It is a reminder that evolution often favours edges, the boundaries where contrasts meet. When we stand today on those same shores, Watching the tide slide out across rocks glistening with life, we are looking at the same clock that guided our ancestors through the hardest of ages. The mussels that feed seabirds now are the descendants of those that fed humans then. The cycle of tides remains unbroken, a rhythm stretching back through volcanic winters and interglacial warmth alike. What if the first safe place was simply where the tide went out? Then survival was not a conquest of new worlds, but a rediscovery of the old, an understanding that safety can live in the smallest patterns, in the twice-daily heartbeat of the ocean. The coastlines that once sheltered our species are still there, whispering with every retreating wave that endurance is often found at the edges of change. Imagine raising a child beneath a sky that never quite clears. The air is cold but not bitter, grey but never entirely dark. Each morning looks like twilight, and each evening comes too soon. 70,000 years ago, this was the new normal. The volcanic haze that had dimmed the planet after Toba did not simply vanish when the ash settled. It lingered, mingling with dust from dry plains and aerosols from the cooling seas. The Earth had entered a long memory of cold, a climate that never fully recovered, only learned to endure itself. For those living in the refuges that remained, the seasons became indistinct, the world quieter, the light thinner. The Great Eruption was already history, but its aftershocks played out in the sky, in the soil, and in the rhythm of life. Vegetation had shifted toward hardier species. Grasses and shrubs replaced broad forests. Rivers flowed weaker and cooler. The wind carried fine particles across the continent, whitening the horizon. The climate models we run today suggest an average global cooling of 3 to 5 degrees, but that number conceals the lived reality. Winters that stretched longer each year, summers that barely warmed, and clouds that refused to move on. In such a world, adaptation meant not innovation for its own sake, but endurance by design. The landscape rewarded those who learned to live within its limits rather than fight them. Hunting and foraging followed tighter patterns, shorter forays, longer stays near dependable water. Families moved less often, staying close to refuges that offered shelter from wind and access to predictable resources. The caves along the coasts, once temporary camps, became semi-permanent homes. Fire became not just warmth, but rhythm, marking the difference between day and night in a sky that no longer cooperated. Archaeological sediments from this period in southern and eastern Africa show an intensification of occupation layers, thicker accumulations of ash and refuse within caves, and more compact hearth sequences. Each layer of soot and shell represents the slow adjustment of people who no longer expected the climate to heal. The volcanic winter had become habit, a stable instability to which life adapted. Toolmaking shifted subtly. Materials had to last longer because suitable stone was not always within reach. In cooler, drier conditions, the movement of groups across landscapes narrowed, limiting access to specific quarries or riverbeds. The tools that survived this era show a preference for harder, finer-grained stones, quartzite, chert and silkrete, materials that could be resharpened again and again. Instead of rapid replacement, tools were repaired, reshaped, curated. Efficiency became culture. A single blade might serve for months, reworked until it was smaller than a thumb. Shelter also evolved in quiet ways. Evidence from fire residues and spatial distribution of artifacts in coastal caves suggests that living areas were increasingly organised. Separate hearths for cooking and warmth, designated spaces for sleeping and tool-making. Over time, this organisation hints at social routines adapted to confinement. In a world of shortened days, the interior of a cave was both refuge and universe. The glow of firelight reflected on rock walls, mixing orange with grey. Smoke stains above the ceilings mark the persistence of occupation across centuries of ash and wind. Environmental proxies tell us that these were decades and centuries of cold equilibrium. Pollen recovered from lake sediments in South Africa shows the spread of grasses adapted to aridity and frost. Isotope ratios in stalagmites from caves like cold air show lowered temperatures and reduced rainfall, aligning precisely with the post-Toba interval. The climate did not swing violently anymore. It settled into a long plateau of cool dryness. To modern humans accustomed to change, this might have felt like stability, but for ecosystems it was constraint. Every species, human or otherwise, learned to operate on reduced energy. Even the ocean played differently. Cooler surface waters decreased evaporation, altering rainfall patterns inland. The sea still offered food, but currents shifted subtly, driving colder water farther north and concentrating marine life along narrower belts. Those who lived along the coast followed the pulse of the ocean, timing their gathering to the new patterns of tide and wind. Inland, herds of grazing animals migrated erratically, chasing vegetation that no longer grew where it once had. The rules of tracking and timing changed, and with them the habits of hunters. To raise children in this dim world meant teaching caution and memory rather than expansion. Knowledge of edible roots, of safe water, of winds that carried ash, all became inherited survival codes. Parents who once might have moved freely across open landscapes now taught their young the geography of scarcity, where the fog thickened in the mornings, where the tide left the fattest mussels, which direction to face a shelter to catch the last warmth of the low sun. Adaptation was not an act of genius, but of patience, written into the daily acts of care. Across generations, that patience shaped physiology as well as behaviour. Cooler, drier air favoured endurance over speed, conservation of heat over expenditure of energy. Some researchers have suggested that prolonged exposure to low light could have influenced pigmentation, metabolism, even circadian rhythms, though such connections remain speculative. What is clearer is that selection favoured resilience. Bodies and minds able to thrive in marginal conditions. The environment pressed for balance, not brilliance. The archaeological signatures of these pressures are subtle but visible. Increased use of shelters and durable materials implies that people were investing more in place than in movement. Hearths reappearing in the same spot across centuries suggest cultural memory, the passing down of locations known to work. In some sites, repeated use of the same cave entrance shows that knowledge of microclimate and wind direction was preserved over generations. Survival depended on recognizing the patterns that persisted when everything else changed. This prolonged cooling also deepened the ecological divide between regions. The interior of Africa grew harsher, deserts expanding, while coasts remained comparatively stable. Populations that had once exchanged goods or mates across wide distances became increasingly isolated. Over time, this fragmentation might have encouraged local adaptation, creating genetic and cultural diversity within Africa long before any later expansion beyond it. Each enclave developed its own rhythm, tuned to local resources, all within the same overarching chill. For the plants and animals sharing this world, the effects were equally profound. Megafaunal species adapted to open savannas began to move along the coastlines, following green corridors. Small mammals and birds clustered in wetter refuges, creating dense pockets of biodiversity in an otherwise thinned-out landscape. Humans would have hunted and gathered alongside these shifting ecologies, their survival intertwined with the resilience of other species. From a climatic standpoint, the persistence of volcanic cooling illustrates how sensitive Earth systems can be. Once aerosols and albedo feedbacks were established, the planet remained in a self-reinforcing loop. Glaciers advanced, reflecting more sunlight. Dust from drying lands further cooled the atmosphere. Even after the direct influence of Toba's aerosols faded, the secondary effects carried on. The planet had found a new equilibrium, one colder, drier, dimmer, but stable enough to live in. The endurance of human groups through this extended chill demonstrates that adaptation need not be dramatic to succeed. There were no grand inventions, no sudden revolutions, only the quiet refinement of daily life. Thicker clothing from animal hides, deeper hearths built to preserve coals overnight, more careful use of wood in regions where trees were rare. Each small adjustment added up to continuity. The archaeological record rewards us with these whispers. Thicker ash layers from longer burning fires, reduced gaps between occupational deposits, and traces of soot in the narrowest crevices of rock shelters. These are the fingerprints of persistence. By 70,000 years ago, the survivors of this dim epoch had learned to live with the grey. The younger generations no longer remembered a world of warmth or bright light. For them, the constant cool haze was simply the way things were. They grew up knowing how to find comfort in the small heat of fires and the steady rhythm of tides. To them, the volcanic winter was not a crisis but a climate, a reality woven into every decision and story. In the long view of prehistory, this period stands as one of quiet recalibration. Humanity, constrained and slowed by the planet's own shadow, learned an essential lesson: that survival is less about abundance than about adaptation to scarcity. Those who stayed by the coasts, those who made tools that endured, and those who built fires that lasted through endless grey dawns, all contributed to a lineage that would one day outlive the cold. The world had not yet brightened, but life had stabilised within its twilight. The ash had fallen, the dust had settled, and the children raised beneath that dim sky would become the ancestors of resilience. The volcanic winter had become habit, and in its patience, humanity learned how to live in the long grey rhythm of endurance. Imagine standing in a land where the sky has fallen. The air is heavy with silence, the rivers move sluggishly beneath layers of grey, and the soil itself has turned to ash. 74,000 years ago, the Indian subcontinent was as close to ground zero as any place on Earth could be. The Toba eruption, born just across the Bay of Bengal, had buried much of the region under clouds of volcanic dust. Yet somewhere within that landscape, beneath layers of destruction now hardened into stone, there are signs that life, and perhaps even human life, did not vanish. When researchers first traced the distribution of Toba's ash, they expected to find a continental graveyard. The eruption's magnitude had ejected billions of tons of tephra, spreading a layer up to 15 centimetres thick across much of India. In some valleys it reached far deeper, filling basins and rivers like cement. Even today, geologists can walk along ancient cuttings and see the line of pale grey running unbroken through the red soils, a visible scar of the planet's largest known eruption. It divides time neatly, before Toba and after Toba. What startled scientists, however, was what they found beneath and above that line. At 𝐓𝐈𝐌𝐄𝐒𝐒, a series of rock shelters and open-air sites in the Kurnool district of southern India, archaeologists began excavating in the early 2000s. There, among layers of river gravels, they encountered the unmistakable horizon of Toba ash, fine, compacted, light-coloured sediment several metres thick. Beneath it they found stone tools, large hand axes, cleavers and flakes typical of what prehistorians call the Acheulean tradition, a technology that had been used by hominins for hundreds of thousands of years. Above the ash, they found something else, smaller flakes and points, more refined, more deliberate. At first glance, this shift looked like a rupture, but the more carefully scientists examined the layers, the less clear the break became. There were no signs of long abandonment between the pre- and post-ash deposits. The sediments were continuous, the soils undisturbed, the tools seemingly part of a steady sequence of occupation. In other words, whoever had been living there before the eruption might have been there afterward as well. This continuity suggested something remarkable: survival at the edge of catastrophe. If the populations in southern India endured the ashfall, they did so at the epicenter of one of the harshest volcanic winters in human history. But the evidence at 𝐓𝐈𝐌𝐄𝐒𝐒 refused to fit the old assumption of total devastation. It told a quieter story, of persistence through transformation. The key lies in how ash behaves once it settles. Unlike lava or pyroclastic flows, which destroy everything in their path, ash can vary in its impact depending on moisture, wind and vegetation. In regions with thick canopy or well-watered soils, the ash may have accumulated gently, sealing rather than sterilising the ground. Over time, rain leaches out toxic elements and restores fertility. Some areas, especially those near rivers and lakes, recover within decades. The environment around 𝐓𝐈𝐿𝐼 likely offered such microclimates, valleys where ash mixed with water to form protective muds, shielding roots and seeds from total desiccation. When the first surveys were published, debates erupted almost as fiercely as the volcano itself. Could humans really have survived in India under that much ash? Some researchers argued that the tools found above the layer must have belonged to later arrivals, long after the eruption. Others pointed to the stratigraphy and insisted on continuity. The truth, as often in prehistory, lies in the nuances between certainty and possibility. The ash at 𝐓𝐈𝐿𝐼 has been dated precisely to the Toba eruption through geochemical fingerprinting, matching its trace elements to the known composition of Toba's ejecta. The tools below and above it, however, are more difficult to date. No bones, hearths, or organic material survive the pressure of time. Instead, archaeologists rely on luminescence dating, which measures when minerals in sediments were last exposed to sunlight. Those readings place both tool assemblages around the same general period, before and just after 74,000 years ago, overlapping within the margin of error. If correct, that overlap means that the same population, or at least the same cultural tradition, endured the ashfall. These were people already accustomed to surviving in semi-arid conditions. Their riverine habitats offered fish, mollusks, and the occasional large game. The transition from Acheulean to Middle Paleolithic technology in India, smaller flakes and points replacing large bifaces, might reflect adaptation to scarcer resources. In a colder, dustier world, smaller, more efficient tools made sense. The Toba ash, ironically, helps preserve this record. Its fine texture seals what lies beneath from later erosion, acting like a geological bookmark. Across India, dozens of such sites now show the same pattern: an ash layer, and beneath it, traces of pre-eruption life. Above it, often within a few centuries, evidence of renewed occupation. In some areas, the ash may have thinned quickly; in others, it lingered, reshaped by wind and rain into dunes of pale silt. But everywhere it carries the same message. Recovery was faster than once imagined. The human presence that endured in India during this time was not necessarily large. Population densities were likely minimal, restricted to favourable environments: river valleys, lake margins, and coastal corridors where microclimates softened the volcanic chill. Yet even a handful of surviving groups is enough to maintain continuity. The key factor would have been adaptability to mosaic landscapes, where small patches of fertility persisted within a wider desolation. At 𝐓𝐈𝐌𝐿 and nearby sites, microscopic analyses of sediments reveal that vegetation returned relatively quickly. Pollen samples show a brief decline in tree species followed by recovery within a few hundred years. That rebound may have created windows of habitability sooner than expected. For people already adapted to flexible foraging, those windows were lifelines. There are also hints of fire use in these deposits: charcoal flecks and burned stones within and just above the ash. If these features represent human hearths rather than natural fires, they would mark an extraordinary continuity of occupation through the eruption's aftermath. Fire, once again, becomes the emblem of persistence. The Indian subcontinent's position may have helped. Prevailing winds carried much of Toba's heaviest fallout westward and northwestward, but the monsoonal patterns that normally brought rain from the Indian Ocean might have shielded certain regions from the thickest deposits. Modelling studies suggest uneven coverage, with central and northern India receiving deep accumulations while parts of the south experienced less intense ashfall. Local topography would have further complicated the pattern. In such variability lay survival's chance. Over the decades since 𝐓𝐈𝐿𝐼𝐼's discovery, other sites have joined the puzzle: Middle Sun Valley, Didwana and 𝐓𝐀𝐌𝐿𝐌𝐄𝐒 Valley, all showing signs of continuity across the Toba layer. Each adds another fragment to the emerging picture of resilience. The Acheulean Middle Paleolithic transition, once thought to reflect the replacement of archaic populations by newcomers, may instead record a local evolution, a response to stress rather than invasion. What these findings collectively imply is that the human story in India did not pause at 74,000 years ago. The subcontinent was not a wasteland swept clean by volcanic fury, but a living laboratory of endurance. Ash did not erase life, it reshaped it. Beneath its weight, ecosystems fractured, adapted, and reassembled. Hominins, whether early Homo sapiens or other closely related forms, found ways to adjust, just as the land itself did. The continuity of lithic traditions across the Toba boundary is, in a sense, the archaeological equivalent of a heartbeat. Each flake of stone struck above the ash echoes the rhythm of those struck before it. Together they form a pulse that bridges catastrophe, a signal that the lineage of survival extended unbroken even through the darkest years. The story of India under the ash is therefore one of paradox. Here, at the epicentre of devastation, we find the clearest signs of resilience. The very place where extinction seemed inevitable became a refuge of continuity. The survivors may have been few, their world grey and fragile, but the evidence they left behind whispers something profound, that the capacity for endurance was already deeply encoded in our lineage long before the skies cleared. When scientists kneel today in the dusty beds of 𝐓𝐈𝐿𝐼𝐼, brushing away the same pale powder that once fell from the sky, they are touching both ends of a story, the chaos that buried the land and the quiet persistence that rebuilt it grain by grain. Could anyone have survived Ground Zero? The stones suggest they did, and in doing so they remind us that life's most extraordinary triumphs often unfold not in abundance, but in the patient work of simply not disappearing. Imagine an island chain where the sky rains glass. 74,000 years ago, the volcano that would become Lake Toba tore open the crust of Sumatra and filled the air with molten dust. The islands of Indonesia, Sumatra, Java, Borneo, and the smaller stepping stones of 𝐓𝐈𝐌𝐄𝐒𝐒 became laboratories of survival. Some vanished beneath ash, others only darkened for a time, and a few, against all odds, remembered how to live. From the moment the eruption began, the islands nearest the source were drowned in fire. Pyroclastic flows swept down the Sumatran valleys faster than sound, vaporizing forests and turning rivers into boiling slurry. Entire ecosystems disappeared within hours. Ash clouds drifted eastward, settling over Java and Borneo, coating leaves, rivers, and animal hides in a grey powder that blocked sunlight and poisoned the soil. What had been a patchwork of rainforests, mangroves, and volcano-fed plains became a dull mirror of itself, silent except for the wind moving through dead trees. And yet, life did not vanish completely. Beneath that silence, some species found shelter in places the eruption could not reach. Coastal caves, deep valleys, and shaded ravines where moisture lingered. Seeds buried in ash germinated when rains returned, and new forests, thinner but stubborn, rose on the fresh volcanic soil. The recovery would take centuries, but recovery began almost immediately. The Toba eruption was not the end of these islands. It was the beginning of their long memory. Sumatra bore the brunt of the blast. The caldera it left behind, more than 100 kilometres wide, would eventually fill with water to form the vast lake we know today. But beyond its immediate reach, much of the island remained biologically connected to its neighbours. Ashfall blanketed the western and northern regions in layers tens of centimetres thick, yet the far south may have escaped complete devastation. Fossil pollen records show that vegetation declined sharply, but rebounded within a few thousand years, a geological blink. Volcanic soils, rich in minerals, supported quick regrowth once the air cleared. Java, lying just to the southeast, tells a slightly different story. There, the ash layer was thinner, perhaps only a few centimetres, but its effects were profound. The eruption altered river systems, redirected drainage basins, and reshaped coastlines. Fossil assemblages from this period reveal a transition in fauna. Species that had thrived in dense tropical forests gave way to those suited for more open, drier environments. Giant bovids, elephants, and deer species replaced forest-dwelling primates and smaller mammals. The Toba eruption may not have caused this turnover on its own, but it accelerated a shift already in motion. Climate cooling and volcanic dust combined to remake the island's ecosystems into a mosaic of grassland and sparse woodland. Among these shifting ecologies lived a remarkable caste of hominins. On Java, the long-lived population known as Homo erectus may have survived well into this period, though evidence grows thin after around 100,000 years ago. Whether any of them witnessed the eruption is unknown, but if they did, they would have seen their world transformed almost overnight. Volcanic glass and acid rain would have stripped vegetation, forcing them to move toward surviving patches of forest or coast. The changing fauna would have challenged their hunting and scavenging strategies, perhaps hastening their decline. In this sense, Toba might have been their final teacher, the event that ended one lineage even as it set the stage for another. To the east, across deep ocean channels, lay the scattered islands of 𝐓𝐈𝐌𝐄𝐒𝐒, Lombok, Sumbawa, Flores, Sulawesi, and Timor. These islands were isolated by waters too deep to have been bridged even during the lowest sea levels of the Ice Age. They formed a separate evolutionary world, where animals and hominins evolved in splendid isolation. On Flores lived the small-bodied species Homo floresiensis, sometimes called the Hobbit, already distinct from other humans by hundreds of thousands of years. The Toba eruption reached even here, but in diminished form, fine ash rather than fire. Excavations in 𝐓𝐈𝐌𝐿𝐄𝐒𝐒 cave, where the remains of H. floresiensis were found, contained traces of volcanic material dating roughly to this period, yet the species persisted afterward. How such fragile populations survived remains uncertain. The caves of Flores and other islands provided shelter, but food chains would have been disrupted. Ashfall would have smothered vegetation, reducing the availability of fruit and prey. Perhaps these isolated hominins relied on coastal resources as modern humans later would. Shellfish, fish trapped in tidal pools, crabs hiding in mangrove roots. The volcanic haze may have darkened their skies, but it could not erase the rhythm of the tides. In the seas between these islands, new landscapes emerged and vanished with each drop and rise of sea level. During the colder phases following Toba, vast stretches of the Sunda Shelf, the continental platform connecting Sumatra, Java and Borneo, were exposed as dry land. Rivers that once flowed separately merged into massive systems, creating fertile floodplains fed by volcanic minerals. These corridors may have become pathways for animals recolonizing the islands after the eruption. Fossil evidence shows that species such as Stegodon, a small relative of elephants, reappeared in Java and Flores after the volcanic dust settled. The archipelago remembered life and rebuilt it, one migration at a time. Paleontologists studying Java's faunal layers notice another intriguing pattern. While many species vanished, others adapted by shrinking in size, a phenomenon known as island dwarfism. When resources are scarce and competition intense, smaller bodies require less energy. The same process that had already miniaturized the hobbits of Flores may have played out among other species after Toba, creating compact versions of once mighty creatures. Even the great tigers and elephants of Southeast Asia might have retreated into smaller, leaner forms. Nature's response to catastrophe was not destruction, but redesign. Tephra analysis across the region shows the reach of Toba's breath. In marine cores near Java, thick bands of ash mark the eruption's timing, each layer chemically identical to the material found in India and East Africa. Yet beneath those layers, life resumes without pause. Foraminifera, tiny marine organisms whose shells record environmental conditions, show only brief disruptions in growth. Within a few decades, the ocean plankton had recovered. The sea, indifferent to our dramas, remembered how to feed itself. In the terrestrial realm, vegetation recovered unevenly. On Sumatra and Java, forests slowly re-established along wetter ridges, while open grasslands expanded elsewhere. This mosaic created new ecological opportunities. Grazers spread into the cleared lowlands, predators followed. The old equilibrium of tropical rainforests gave way to dynamic landscapes full of flux. It was within these landscapes that any surviving hominins, whether erectus or early sapiens, would have adapted. Some archaeologists suggest that early humans may have reached these islands earlier than previously believed, possibly before the eruption, using primitive rafts or island-hopping routes across the narrow straits. If so, then Toba did not erase their presence, it simply reduced it to whispers. No clear fossils from this precise window have been found, but stone tools from Sulawesi and Flores hint at continued human activity through the post-eruption millennia. Whether these were descendants of earlier arrivals or survivors of local species like Homo floresiensis, they represent continuity amid isolation. The islands also preserved memory in stone. Volcanic layers act as datelines for the Earth's story, locking within them traces of temperature, rainfall and chemistry. Each layer across the Indonesian archipelago tells a slightly different version of the same event, thicker near Sumatra, finer toward the Pacific. Reading these strata is like listening to an echo fading across distance, the same song of fire played at lower volume. What emerges from this geological and biological record is not a single narrative of devastation, but a patchwork of survivals. Some regions of the archipelago were sterilized, others bruised, still others barely touched. The diversity of outcomes mirrors the diversity of islands themselves. Indonesia's complexity, the very reason it's so rich in life today, was its salvation even then. No single disaster could erase it all. The story of the islands that remembered is, at its heart, a meditation on resilience through fragmentation. The Toba eruption bound this chain of lands into a shared trauma, yet each island responded in its own way. Sumatra scarred but fertile, Java transformed and reshaped, Wallacea isolated yet persistent. Flores, with its hobbits and dwarf elephants, outlasted the storm entirely. Each held a different version of survival, like verses in a song that the earth itself refused to forget. When we look today across Indonesia's Emerald Arc, dotted with volcanoes still breathing quietly, we see the legacy of that endurance. The forest that regrew on ash, the coral reefs that recolonized cooled seas, and the species that evolved from survivors of that ancient catastrophe, all are living reminders that memory is built into geology. The islands remember not through words, but through soil, stone, and DNA. So what happens to an island chain when the sky rains glass? It becomes a map of memory. Some parts vanish, others burn, but a few hold on long enough for life to start again. The ash becomes soil, the scars become landscapes, and the survivors, whether elephants, hobbits, or quiet forest seeds, become the storytellers of a planet that never truly forgets. Imagine the first footprints pressed into cold sand, the marks of people who had learned not to wait for warmth to return. 70,000 years ago, long after the sky had dimmed and the volcanic ash had drifted into the oceans, Africa was still a continent living under a slow chill. The climate had stabilised into something drier, harsher and quieter than before. Rivers shrank, grasslands withdrew, and the air carried more dust than rain. Yet in these subdued landscapes, scattered along the coasts and highlands of the south, our ancestors continued their quiet work of endurance. They were not expanding yet, only learning how to stay alive. The archaeological record of this period shows no great revolution, no leap in technology or cognition. Instead, it reveals an unbroken thread of adaptation, small refinements born of necessity, gestures of intelligence honed by scarcity. Sites like Pinnacle Point, Sibudu, and Deep Kloof, scattered across the southern Cape, hold the sedimentary memory of people who faced centuries of cold and did not vanish. Their tools, pigments, and shelters were not symbols of culture yet, but instruments of survival. In the cold that followed Toba, southern Africa's refugia became laboratories of invention. Ocean currents continued to moderate the coastlines, creating small zones of climatic stability amid continental aridity. Climate models show that while the interior turned to steppe and desert, the southern and eastern coasts retained humidity and relatively mild temperatures. These narrow belts of survivable climate functioned as corridors of life, sustaining populations that had already weathered the earlier volcanic dimming. The refugees that once protected small groups now held the core of the species. In these refugees, people began to tinker with stone, pigment, and rhythm. Excavations at Pinnacle Point reveal evidence of heat-treating silcrete, a process in which stone was deliberately heated to improve its flaking qualities. This technique required not just knowledge of fire, but control over its temperature, timing, and context. Heat treating turns dull rock into glassy, sharp-edged material, ideal for producing fine cutting tools. It was a small act of engineering, born not from luxury but from limitation. When high-quality stone became scarce, people learned to transform what they had. At Sibudu Cave, layers from this period contain traces of complex adhesives, mixtures of ochre, plant resin, and powdered stone used to haft stone flakes onto wooden shafts. Chemical analyses show that these compounds were heated and stabilized with astonishing precision. They were not artistic pigments, but functional chemistry, evidence of cognition shaped by necessity. Each innovation reflects a species learning to manipulate materials with deliberate, repeatable control. Ochre itself tells part of this story. Often described as symbolic or decorative, its earliest use may have been purely practical. Red and yellow ochres contain iron oxides that repel moisture, preserve hides, and protect skin from the sun. In cold, dry climates, ochre mixed with fat becomes a natural insulator. It can also act as an adhesive stabilizer or insect repellent. The people of this era may have worn pigment not to adorn themselves, but to survive, to weather the bite of the cold, the sting of insects, and the glare of a pale, dust-bright sky. Archaeologists at Deep Kloof Rock Shelter found fragments of ostrich eggshells engraved with cross-hatched markings, dating to roughly this period. While their meaning is debated, the physical evidence suggests familiarity with the material's texture and strength. These eggshells were used as water containers, lightweight, durable, and refillable. In a drying world, water storage meant continuity between seasons, between droughts, between generations. The engravings may have marked ownership or measurement, but even without symbolism, they represent planning, the ability to imagine a future that needed provisioning. The patterns of habitation at these sites reveal another quiet adaptation, cyclical return. Rather than nomadic wandering, groups seem to have practiced a seasonal rhythm, returning to the same shelters repeatedly. Layers of ash and tool debris accumulate like the pages of a calendar, each one a reoccupation of a familiar place when resources allowed. This pattern shows not expansion but intimacy, a knowledge of landscape precise enough to move within its limits without exhausting it. In the broader continent, climate modelling and sediment data from ancient lakes reveal the extent of hardship. Lake Malawi, in East Africa, contracted dramatically, its surface dropping by more than 100 metres. The surrounding basin became semi-arid, leaving only small pockets of aquatic life. Dust records from marine cores off the west coast indicate intensified wind transport, a sign of expanding deserts. Africa, for all its size, had shrunk into a patchwork of microclimates, each sustaining fragments of what remained of humanity. Yet those fragments were inventive. The stone tool industries of this time show experimentation with microliths, small, sharp flakes designed for composite tools. While full microlithic technology would flourish later, the seeds were already present. These miniaturized tools were efficient, versatile, and resource-saving. They could be mounted in series on wood or bone, creating cutting edges or barbed points. The logic behind them was simple but profound: make more from less. In such conditions, every innovation carried a cost-benefit calculation. Each piece of ochre mined, each stone flaked, each fire built represented energy spent that had to yield survival value. Over time, these decisions accumulated into what we now recognize as behavioral sophistication. But at the time, they were pragmatic, incremental answers to the slow cold. Even shelters show this pragmatic creativity. At Sibidu, microscopic plant remains reveal the deliberate use of bedding layers made from reeds and grasses, sometimes topped with aromatic leaves that possess insecticidal properties. These bedding layers were periodically burned to sanitize living spaces, a form of low-tech hygiene practiced tens of thousands of years before the word existed. Such behaviours speak of an awareness of comfort, safety and health that transcends mere instinct. It is survival infused with understanding. When viewed through climate reconstructions, these archaeological fragments gain deeper meaning. Southern Africa's relative stability during the post-Toba cold suggests that its coastal populations not only endured, but may have slowly grown. Stable temperatures, steady access to marine foods, and the availability of plant resources would have supported continuity even as the rest of the continent faltered. Genetic diversity in modern humans still bears traces of this pattern, not because of migrations, but because of ancient persistence. The tools and pigments of this age are therefore not just relics of survival, but indicators of learning under constraint. Every improvement in adhesive chemistry or heat treatment represents a feedback loop between environment and behaviour. The colder the world became, the more finely humans tuned their responses. Evolution favoured memory, planning, and cooperation, the intangible tools that leave no fossils but define our lineage. Even in the bleakest phases, the landscape was not uniformly barren. Climate models suggest pulses of moisture along river valleys and mountain slopes, brief wet intervals when vegetation returned and animals followed. These intermittent reprieves would have structured human movement, drawing groups together and dispersing them again. Such oscillations trained flexibility into our species, embedding variability into our psychology. The capacity to adapt, to improvise, to endure in uncertainty may have taken root in these cycles of scarcity and relief. By 65,000 years ago, the skies had begun to brighten slightly, but the habits forged in the cold remained. People still occupied the same coastal shelters, still harvested shellfish and game, still mixed ochre into their daily routines. Their world was modest, but durable. The very absence of dramatic change is the evidence of their success. They had achieved equilibrium with a planet in recovery. When we sift through the sediments of those ancient refuges, we find no heroes, no grand events, only persistence. Burned seeds, ochre-stained stones, worn flakes, the archaeology of patience. These traces remind us that survival is not always about expansion or conquest. Sometimes it's about waiting, refining, and remembering. The cold trails in Africa were not the path to elsewhere, but the ground on which we learned who we were when movement was impossible. So did survival shape us before expansion ever began? Almost certainly. The mind that would one day cross continents was forged in the quiet laboratories of endurance, in the fire-warmed caves of the southern coast, in the hands that mixed pigment for warmth, in the hearts of those who learned to trust the rhythm of the tide when everything else turned still. Before the world opened, humanity had already learned its first and most essential lesson: how to stay. Imagine that every human alive today is carrying a fossil, not in bone but in code. Hidden deep inside our cells are the quiet echoes of a time when the world nearly went silent. A record not written in ash or stone but in probability. Around 70,000 years ago, as the earth cooled and the skies dimmed, the population of our species shrank to a fraction of what it had been. That contraction, whether caused or only deepened by the Toba eruption, left an imprint so faint that it took the invention of genomics to find it. When scientists began sequencing whole genomes and tracing how genetic variation is distributed among us, they discovered that our diversity is astonishingly small, smaller than that of almost any other mammal of comparable global range. It is as if humanity passed through the eye of a needle and carried the narrowness forward ever since. To understand how that story is told in DNA, we have to think of genes not as static blueprints, but as moving signals through time. Every piece of our genome, every stretch of nucleotides inherited from our ancestors, carries a history of copying, mutation and recombination. When populations are large, these signals branch widely. Mutations accumulate independently, creating a forest of genetic variety. When populations are small, many branches die out by chance, and the forest thins into a single narrow grove. This process is the foundation of what geneticists call coalescent theory, a mathematical way of running evolution in reverse. By tracing modern genomes backward through time, the model estimates how long ago any two sequences shared a common ancestor. The fewer the ancestors, the faster their lines converge. When applied to humans, these models paint a picture of a long contraction, followed by slow recovery. The deepest parts of our genome, the mitochondrial DNA inherited maternally and the Y chromosome inherited paternally, both show signs of having passed through severe narrowing somewhere between 150 and 50,000 years ago. For mitochondrial DNA, the effective population size during that period may have been as low as a few thousand breeding females. The Y chromosome tells a similar story for males. Nuclear DNA, which recombines and thus retains a richer memory, confirms a prolonged period of reduced genetic diversity stretching across tens of thousands of years. Yet the signal is not clean, and that is what makes it fascinating. Instead of a single, catastrophic bottleneck, what emerges is a textured landscape, a tapestry of small, semi-isolated populations exchanging genes, occasionally across Africa. The pattern of linkage disequilibrium, the statistical association between nearby genetic variants, reveals that some groups were separated long enough for unique combinations of alleles to form, only to reconnect later. Imagine the continent as a network of islands of humanity, sometimes linked by low tides of contact, sometimes separated by deserts and drought. The genome remembers this as clusters of shared ancestry, pockets of similarity separated by stretches of difference. This structure explains why the genetic evidence for a Toba bottleneck remains debated. If human populations were already subdivided before the eruption, then the loss of diversity afterward may reflect demographic isolation rather than extinction-level collapse. Each region could have experienced its own contraction, preserving a distinct subset of the ancestral gene pool. When these lineages reconnected in later millennia, their genetic traces blended into the pattern we see today. Reduced overall diversity but complex internal texture, coalescent models reconstruct these dynamics not from fossils, but from mathematical ghosts. By simulating millions of potential genealogies, the models compare them to the observed frequencies of genetic variants. The best-fitting scenarios reveal not only approximate population sizes through time, but also fluctuations in connectivity between groups. In humans, the signal that corresponds to the 70,000-year window shows both a global dip in diversity and increased regional differentiation, consistent with a world fragmented by climate and geography. What these models cannot tell us is intent. The genome records survival, not experience. It does not remember hunger, migration, or the sound of wind against ash-covered cliffs. It remembers only the numbers, how many individuals passed their genes on, and how often they intermingled. From this mathematical silence, scientists infer that the number of humans may have dropped to as few as several thousand effective individuals, meaning those who actually contributed descendants for a period lasting centuries or millennia. The true population would have been larger, but the genetic effective size translates the messy reality of family trees into the language of probability. The caution, of course, lies in the word effective. It is not a census count, but a measure of how much variation survives through time. Two populations could have identical head counts, and yet very different effective sizes depending on how they mate, move, and subdivide. In a species like ours, where geography and social structure influence who reproduces with whom, effective population sizes can underestimate the number of living individuals by an order of magnitude. The genome remembers relationships, not faces. Still, the overall pattern is unmistakable. Compared with chimpanzees, bonobos, or even gorillas, modern humans carry far less genetic diversity. A single community of chimpanzees can harbour more variation than the entire human species. This uniformity is one of the strongest pieces of evidence that our ancestors endured a long period of low numbers and isolation, a crucible that homogenized their genomes while sharpening their adaptability. Small populations amplify the effects of selection. Beneficial mutations can spread quickly, while deleterious ones vanish more easily. In that sense, the same constriction that nearly erased us may also have accelerated the fine-tuning of traits that later enabled survival in diverse environments. Yet even this idea must be held gently. The genome is not a diary of intentions, it is a record of outcomes. When scientists peer into the depths of mitochondrial lineages or reconstruct ancestral haplotypes, they are not uncovering a single moment of disaster, but a continuous interplay between chance, environment, and time. The narrowness of our diversity may reflect not one storm but many, repeated squeezes of climate and geography over hundreds of millennia. Toba was only the loudest. To visualize this genomic memory, imagine the ancestral population as a braided river. In wide, warm ages, the channels spread and interweave, carrying new mutations far and wide. In cold or arid times, the channels shrink and split apart, some drying entirely. When the flow returns, the surviving channels merge again, blending their sediments. Today's human genome is the delta of that ancient river, a mixture of sediments from channels that almost closed. Coalescent models trace the river backward, watching the branches converge until only a few tributaries remain. Those tributaries are our most recent common ancestors, living in a time when the world was grey, and the population small enough that every child's birth mattered to the species' future. One of the most intriguing signatures left by this contraction is the pattern of long haplotypes, stretches of DNA inherited together because not enough generations passed for recombination to break them apart. In populations that remain large and stable, these blocks are short, eroded by time and mixing. In populations that have passed through bottlenecks, the blocks are longer, reflecting their recent common origin. When geneticists measure these patterns across the human genome, they find evidence of such extended linkage, consistent with a constricted past. The genome, like sediment in a cave, holds layers of closeness still unweathered by age. Modern computational methods refine these timelines using mutation rates, calibrated by ancient DNA from fossils and radiometric dating of divergence events. While estimates vary, most suggest that the deepest shared ancestry among all living humans coalesces around 200,000 years ago, with a pronounced reduction in diversity beginning roughly 70,000 years ago and slowly reversing thereafter. This pattern aligns broadly with the climatic downturns following Toba, though it cannot prove causation. What it does show is that genetic drift and isolation left scars that remain visible even now, faint but measurable in every genome. These models remind us that our DNA is not just personal inheritance but planetary record-keeping. Each base pair has survived countless cycles of replication, error and correction. Each mutation that did not kill or hinder became part of the silent archive of life's persistence. When scientists map genetic variation across modern populations, they are effectively reading a palimpsest, a manuscript overwritten countless times but still bearing the faint ink of earlier worlds. And yet, even with all our sequencing power, uncertainty remains immense. Mutation rates vary, demographic assumptions shift, and the models depend on how we define population. The further back we look, the blurrier the picture becomes until what remains is less a history than a shadow. The genome whispers of smallness, not extinction, of endurance, not triumph. When we ask how much of that darkness still lives inside us, the answer is both literal and metaphorical. The genetic narrowing that once nearly erased our lineage still shapes our biology today. From our vulnerability to disease to the subtle patterns of immunity and metabolism that reflect our shared ancestry. But more deeply, the story embedded in our genomes is one of constraint transformed into continuity. Every living human carries evidence that the species once survived on the edge of disappearance and then multiplied until that memory became diffuse. The storm ended tens of millennia ago, but its signature remains in the code that builds our bodies. It reminds us that we are not the product of abundance but of endurance. Our genomes do not celebrate victory, they record survival. Beneath every strand of DNA lies the quiet arithmetic of persistence, the genetic echo of a world once reduced to whispers. Imagine a planet that never truly went back to the way it was. The ash settled, the air cleared, the skies brightened, but the world that followed the Toba eruption was not the one that came before. Forests regrew, yes, but not in the same places or forms. Rivers found new paths through altered ground. The atmosphere calmed, yet the rhythms of rainfall, temperature and season had shifted into unfamiliar patterns. Recovery, if it can be called that, did not mean restoration. It meant transformation. Between 70,000 and 60,000 years ago, Earth settled into a quieter but stranger equilibrium, a climate that remembered what had happened and never quite forgave it. Geologically, the planet's systems had been jolted. When Toba released its vast plume of sulfur and ash into the stratosphere, it didn't just darken the sky, it altered how sunlight and heat were distributed. For years afterward, the surface cooled, glaciers expanded and the feedbacks began. White ice reflecting sunlight, dust storms amplifying dryness, ocean currents hesitating in their usual routes. Even after the volcanic aerosols had fallen back to Earth, the cooling they initiated persisted through inertia. The oceans took centuries to reabsorb the imbalance. In this new order, ecosystems began to drift away from their pre-eruption baselines. The tropical belts, once thick with rainforests, contracted, and savannas widened across continents. Regions like Equatorial Africa, South Asia, and Southeast Asia became patchworks of mixed habitats, mosaics of grassland, shrub, and remnant forest. Species that had evolved to live in dense canopies found themselves stranded in fragments of green amid expanses of open land. Others, better suited to grazing and movement, began to expand. The result was not extinction at once, but ecological rearrangement, a slow, uneven shuffling of life's deck. Pollen records from lake sediments tell this story in microscopic detail. In cores drawn from ancient lakes in Africa, India and Indonesia, scientists find abrupt declines in tree pollen followed by gradual rises in grasses and hardy shrubs. This replacement didn't reverse. Even when conditions later warmed, the balance of species had shifted permanently. The old forest did not return. New forests made of different assemblages took their place. This was not resilience in the sense of recovery, but evolution in motion. Ecosystems recalibrating to a cooler, drier planet. For megafauna, the New World was both a challenge and an opening. The large mammals of the late Pleistocene had been living near their limits already, highly specialized grazers, browsers, and predators adapted to specific climates. When those climates changed, the fragile balance between species cracked. Some animals migrated, others adapted, and many vanished locally. In South and Southeast Asia, fossil deposits show that species such as Stegodon, giant bovids, and certain rhinoceroses declined in number after the Toba interval. The cooling likely reduced plant productivity, which cascaded up the food chain. Yet for other creatures, disturbance brought opportunity. Open grasslands favoured grazers like antelope, equids, and smaller herbivores that thrived on patchy vegetation. In their wake followed predators, leaner, faster, more adaptable carnivores capable of shifting diets. The ecosystems that emerged during these millennia bore the imprint of selection for flexibility. The animals that survived were those that could endure scarcity, migrate across distance, and exploit multiple food sources. In evolutionary terms, the Toba event acted as a global sieve, filtering specialization out of the biosphere. The hydrological system changed too. With cooler oceans and expanded ice sheets, evaporation patterns shifted. The monsoons that once brought reliable rain to South Asia and parts of Africa weakened, and seasonal rainfall became unpredictable. Rivers that had flowed regularly for tens of thousands of years began to alternate between flooding and desiccation. Lakes receded into smaller basins, leaving behind salt flats and ephemeral wetlands. Some inland seas, like those in East Africa, dropped dramatically in level, transforming fertile valleys into dust plains. The landscapes that later humans would cross were shaped by this long memory of dryness. Scientists studying stalagmites, the slow-growing mineral archives inside caves, can read these fluctuations like barcodes. Oxygen isotope ratios vary with rainfall, and the records from sites in Africa and South Asia show prolonged intervals of aridity after 70,000 years ago, punctuated by brief partial recoveries. The climate system had found a new beat, slower and more irregular than before. This variability would persist for tens of millennia, defining the backdrop for every species still alive, including us. Vegetation structure responded accordingly. Fire became a constant ecological presence. In grass-dominated systems, lightning ignited frequent burns that recycled nutrients and maintained open terrain. Charcoal fragments in sediment cores increased markedly after Toba, indicating a world more flammable than before. Fire regimes shaped plant evolution. Species with fire-resistant bark, underground bulbs, or seeds, triggered by heat, began to dominate. In a sense, the planet became more resilient by becoming more combustible. Disturbance was no longer an exception, it was the rule. Across continents, evolutionary pathways began to diverge in response to this instability. In Asia, cooler climates favoured animals with thick fur and compact bodies. In Africa, the spread of grassland selected for endurance and mobility. Even insects and small vertebrates show morphological changes consistent with adaptation to drier, more open environments. The Toba event had not merely thinned populations, it had restructured selective pressures across ecosystems. The survivors, whether plant or animal, carried the genetic memory of those pressures forward. One striking example of this lagged adaptation can be seen in the forests that eventually reoccupied volcanic regions like Sumatra and Java. Today, these jungles are lush and green, but beneath their soils lie thick bands of Toba ash. Radiocarbon dating shows that forest recovery took thousands of years, an ecological lifetime. When vegetation did return, it was dominated by pioneer species, fast-growing trees with broad ecological tolerances capable of colonizing nutrient-poor substrates. These species laid the groundwork for the diverse ecosystems that followed, but the composition never reverted to its pre-eruption state. The forests of modern Indonesia are, in that sense, second-generation ecosystems born from catastrophe. Marine environments also show signs of disturbance. The vast injection of ash and dust into the atmosphere affected ocean chemistry through ion fertilization, a process where windborne particles stimulate algal blooms. In sediment cores from the Indian Ocean, scientists find spikes in microfossils of plankton following the eruption, followed by declines as nutrient pulses subsided. The temporary productivity boost likely drew carbon from the atmosphere, reinforcing the cooling trend. Even here, the pattern of feedback and adaptation played out, short-term abundance leading to long-term adjustment. Evolutionary biologists often speak of adaptive radiations following mass disturbances, bursts of diversification when new niches open up. The Toba interval may have been one such window, not on a mass extinction scale, but in miniature. As species disappeared from certain habitats, others expanded to fill the void. Birds that could exploit both forest and savanna spread widely. Small mammals capable of flexible diets proliferated. The world became a stage of generalists, less specialized but more numerous in form. This restructuring had profound implications for energy flow. With less vegetation cover and lower precipitation, carbon cycling slowed. Dust from newly exposed soils increased atmospheric particulates, reinforcing cooling. Glacial feedbacks on the northern continents deepened, locking more water into ice and lowering sea levels by tens of meters. The shallower seas around Asia and Africa exposed continental shelves that would later serve as migration corridors, but at the time they were barren plains swept by wind. The Earth, in other words, entered a long pause. From 70,000 to 60,000 years ago, there was no true recovery in the ecological sense. Life went on, but under new rules. Forests were thinner, rivers more fickle, animals more cautious. Every species, from algae to elephant, had to live within narrower margins. The biosphere became leaner, its excess trimmed away by time. For geologists, this era reads as an inflection point, a shift from one equilibrium to another. Before Toba, the planet was warmer and wetter, still resonating with the interglacial pulse of earlier millennia. After Toba, it settled into a cooler mode that would dominate until the end of the Pleistocene. It is as if the eruption triggered not just a temporary winter, but a new climatic logic. The Earth that followed was recognisably the same, yet fundamentally altered in its behaviour. The lesson embedded in these sediments is that recovery is not return. Ecosystems rarely rewind to earlier states, they move forward into new configurations. Disturbance, on geological scales, is a form of renewal. The forests that regrew, the rivers that carved new courses, and the animals that adapted all carried traces of the crisis within them. The world that didn't recover became the world we inherited, one calibrated for variability, not stability. By 60,000 years ago, the feedbacks had stabilised. Ice sheets reached new maxima, sea levels dropped, and dust continued to circulate through the atmosphere. The planet had achieved balance again, but not warmth. This new equilibrium set the stage for the next chapters of evolution and movement. Out of that transformed environment, new species patterns emerged, leaner, more adaptable, and ready for the coming age of expansion. What if recovery never meant return? Then what we call stability is merely the long echo of adaptation. The forests, rivers, and creatures that lived through those centuries did not rebuild the old world. They invented a new one in its ashes, and perhaps, in their quiet persistence, they taught the same lesson the planet has repeated since. That survival does not restore what was lost, it redefines what it means to live. Imagine a world where fire no longer wandered. 11,000 years before the present, the embers that had once followed humans through caves, camps, and open plains finally found a home indoors. It was not a discovery. That had happened far earlier, but a domestication, a quiet reordering of how time itself passed. Fire stopped being something you kept alive for survival, and became something that waited for you. The first hearths and ovens of the early Holocene were not only tools for warmth or cooking, they were instruments of rhythm. They tethered people to place and created the first architecture of daily routine. The beginning of a world where time was measured not by the movement of herds or the arc of the sun, but by the cycle of tending, heating, and resting. In the fertile valleys that stretched from Anatolia through the Levant to the plains of Mesopotamia, the end of the last ice age brought both promise and uncertainty. The climate stabilised into something warmer, wetter, and gentler, allowing plants to flourish, and animals to gather in predictable patterns. The humans of this age were no longer drifting hunters, but semi-sedentary experimenters, learning to stay in one place long enough to see the land respond. The hearth became the centre of that experiment, the heartbeat of settlement. Archaeological sites such as 𝐓𝐈𝐌𝐿𝐴, Abu Huraira, and Göbekli Tepe preserve the physical remains of these early domestic fires. Circular stone-lined pits, charred residues of wood and grass, and in some cases carefully plastered surfaces around the fire basins themselves. These were not campfires. They were built into floors protected by walls, maintained day after day. Some had traces of clay or lime coating, suggesting deliberate attempts to manage heat, to prevent the floor from cracking, or to reflect warmth evenly through enclosed space. The hearth had become a design problem, the first act of interior engineering. When people began to live alongside their fires rather than above them, everything changed. The distinction between day and night softened. Warmth extended activity into darkness. The ability to create light and heat on demand allowed for new schedules, new rituals, new kinds of attention. Archaeologists sometimes speak of the domestication of time, and nowhere is that more literal than in the hearth. It demanded a routine, feeding, cleaning, protecting, a rhythm as intimate as breathing. In tending the flame, humans began to live by the clock of combustion. As settlements grew denser, control of fire grew more precise. charred remains from sites across the Near East show increasing use of specific fuel types. People learned which woods burned hot and which smoked less, which produced coals that lasted through the night. Reed, dung, and straw were mixed with wood to create fuel blends that maximised endurance and efficiency. In this chemistry of warmth lay the foundations of domestic life. The fire was no longer only a tool for cooking or defence, it was a companion that structured the day. The hearth also created space, not just physical, but social. Around its circle, people gathered for warmth, conversation, and work. The distribution of artefacts in early Neolithic houses shows clusters of activity radiating from the hearth outward. Food preparation close to the flame, tool-making nearby, sleeping areas at the periphery. The pattern repeats across sites and centuries, suggesting a shared logic. Heat defined proximity, and proximity defined community. Where the fire burned, there was centre. Then came the oven, a deeper domestication still. By around 9,000 years before the present, in places like 𝐓𝐈𝐌𝐄𝐒𝐒 and the Jordan Valley, people were building clay and mud brick domes designed to contain heat rather than release it. These ovens, often plastered with lime or coated with clay slip, could reach and sustain temperatures far higher than open fires. They transformed not only food but the architecture itself. To maintain an oven, you needed walls thick enough to contain it, roofs that could vent smoke, and surfaces resistant to heat stress. The house adapted to the flame, evolving into a thermal organism. Lime plaster is one of the most fascinating byproducts of this transition. To make it, limestone was heated in kilns to temperatures exceeding 800 degrees Celsius, causing it to release carbon dioxide and form quicklime, which was then mixed with water and ash to create a paste. When applied to walls and floors, it hardened into a smooth, durable surface that reflected light and moderated temperature. This was more than decoration. It was thermal control. Archaeological chemistry shows that lime plaster floors helped regulate indoor humidity and warmth, transforming the house into a kind of living shell, part geological, part human. The production of plaster itself required communal coordination. Gathering enough limestone, wood and labour to maintain kilns demanded organisation and planning. In this way, fire extended its reach beyond the household. It became a shared project, a reason for cooperation. The same technology that heated food and rooms also created the infrastructure of early architecture: walls, floors and eventually pottery. Each use of heat deepened the bond between humanity and combustion. But with permanence came responsibility. A fire left untended could consume an entire dwelling. The ruins of early settlements often bear blackened walls and collapsed roofs, evidence that flames sometimes escaped their boundaries. The hearth demanded vigilance. It shaped behaviour, instilling habits of caution, routine and foresight. Every new morning began with the same quiet ritual, coaxing embers back to life, adding fuel, waiting for warmth to spread. That repetition may seem trivial, but it structured consciousness. To control fire indoors was to live by maintenance rather than reaction, to inhabit a world where predictability had to be built and defended daily. Thermal management extended even to the food itself. The consistent heat of ovens allowed for new forms of cooking: slow roasting, baking, fermentation, processes that required patience and timing. Archaeobotanical remains show charred grains and pulses in these early sites, evidence that people were experimenting with recipes, turning raw plants into meals that could last longer and feed more. Warmth, contained and repeatable, became preservation. In that stability lay the first steps towards storage, planning, and ultimately agriculture. By bringing fire indoors, humans inverted the relationship between danger and comfort. The wild world was cold and unpredictable. The interior was controlled and warm. That distinction reshaped psychology as much as architecture. A room with a hearth became an environment of its own, insulated not only from the weather but from time. Outside, seasons changed. Inside, the flame was constant. The sense of continuity it created may have been humanity's first experience of permanence, a kind of temporal shelter. The light of the hearth also changed how people perceived darkness. Instead of fearing night as a time of blindness, they began to use it. Firelight revealed the interior surfaces of walls, objects and faces in ways natural light never could. Shadows flickered, colours deepened, and the texture of daily life took on new dimensions. Some anthropologists suggest that storytelling and symbolic art found fertile ground in this illuminated half-dark, not as acts of religion, but as side effects of having time, warmth, and company. The flame became both literal and cognitive illumination. Yet even as the world warmed at the dawn of the Holocene, humans learned not to trust it. The memory of cold lingered. Hearths became security systems against climate uncertainty, physical reminders that warmth was a resource to be controlled, not taken for granted. Sedentism may have begun not from abundance, but from the desire to preserve the one element that had made the cold years bearable. The architecture of early villages, with their densely packed houses sharing walls, reflects this thermal economy. Each building conserved and borrowed heat from its neighbours. Communities became networks of warmth. Over time, the presence of permanent fire began to mark a new kind of territory. In mobile societies, fire was temporary, something carried and extinguished with each move. In settled ones, it became infrastructure. Archaeological layers reveal clusters of ash and burnt clay that accumulate in the same places over generations, evidence that fires burned continuously in the same hearths for centuries. Some were repaired repeatedly, their stones blackened, their floors replastered. Each repair was a renewal of the pact between humans and flame. The impact on human time perception cannot be overstated. Before, days were measured by light and darkness. After, they were measured by maintenance. How long the coals would last, when to add fuel, when to cook, when to rest. Fire's endurance became the metronome of existence. In some sense, the first sedentary humans did not just build homes, they built clocks that glowed. When archaeologists sift through these ancient floors, they find not only soot and ash, but traces of intention, carefully placed stones, heat-resistant linings, residues of lime and fat. Each hearth is a fossilized moment of care. Together they tell a story not of invention, but of cultivation, a relationship tended through countless small gestures, every one of them ordinary and world-changing. How did controlling warmth reshape time itself? It slowed it down. It gave it walls. The constant fire transformed days into cycles of repetition and rest, anchoring memory to place. In that steady glow, humanity found not just comfort, but the first sense of continuity, the feeling that the future could be managed because the present could be kept warm. Imagine a world where the only sound left was breathing. No words, no songs, only the slow rhythm of survival. Around 74,000 years ago, when the skies dimmed and the forest died back after Toba's eruption, our species may have fallen into one of its quietest ages. Not silent in the literal sense. People still spoke, shouted, sang to children and warned each other of danger, but silent in another way. The connections between groups thinned. The long chains of knowledge transmission that once bound distant bands together snapped, and language itself, still fragile, may have fractured into isolation. In the deep cold and the long dark, human culture might have gone nearly mute. Archaeologists and linguists sometimes describe this period as a behavioural pause, not a regression, but a standstill, a stretch of millennia when symbolic innovation slowed, communication networks shrank, and cultural memory contracted under environmental stress. The evidence is subtle, but it lingers in the archaeological silence that follows the Toba ash. Sites that once show regular toolmaking or pigment processing fall quiet. Occupation layers thin. The Earth between 70 and 65,000 years ago speaks of smaller, more scattered populations, and perhaps of a narrower range of expression. If language had already begun to evolve by that time, and many scientists believe it had, it would have depended on interaction between groups to maintain complexity. Languages change, expand, and diversify through contact. When contact ceases, they ossify. In the same way that genetic diversity contracts during a population bottleneck, linguistic diversity can collapse when communities fragment. The result is simplification. Fewer words, reduced grammar, less nuance. The storm may not only have erased forests and animals, but also syllables, metaphors, and songs. The relationship between language and demography is not hypothetical. Modern linguistic models show a strong correlation between population size, interaction frequency, and linguistic richness. Large, interconnected societies tend to develop elaborate vocabularies, specialized terms, and nested grammar. Small, isolated groups often streamline their languages for efficiency. This is not a measure of intelligence, but of necessity. When survival depends on a few dozen people who already share everything, communication becomes less about abstraction and more about coordination. In such worlds, speech narrows to what must be said. In the aftermath of Toba, isolation was everywhere. Ash and cooling cut travel routes, reduced animal migrations, and made distant contact dangerous. Populations that once exchanged tools, mates, and ideas through long chains of foragers found themselves stranded. Over generations, each group would have developed its own microdialect, its own way of describing the world's dim light and scarce food. But those words would not travel far. The linguistic map of humanity may have fragmented into hundreds of tiny islands, each with its own fading tongue. This scenario is consistent with genetic and archaeological evidence, showing strong regional differentiation during that window. Just as genes diverged when groups stopped interbreeding, languages and behaviours likely diverged when groups stopped meeting. Linguistic evolution and biological evolution are parallel processes. Both require variation, selection, and flow. When flow stops, change continues, but direction becomes random. Some researchers have proposed that this period of fragmentation delayed the emergence of symbolic culture, not because people lacked the cognitive capacity for it, but because the social networks necessary for transmission were broken. Symbolic behaviour, like language, depends on redundancy. Ideas must circulate, be copied, and reinterpreted to persist. In small, stressed populations, innovation tends to vanish as quickly as it appears. If someone invented a new way of marking a tool or a new rhythm of chant, it might have lived and died within one generation. The archaeological record hints at this transience. In layers dated to roughly 70,000 years ago, tool assemblages often show continuity of basic techniques but little innovation. The stone points of this era are functional, repetitive, precise, designed for efficiency rather than experimentation. Some researchers see this as evidence of conservatism, a kind of technological minimalism born of necessity. When resources are scarce and risk is high, you make what you know will work. Creativity is a luxury of abundance. There may also have been an environmental feedback between sound and survival. In an age when the air was filled with ash and the forests muffled by dust, acoustics changed. Open savannas carried sound differently than damp forests. Voices travelled farther, but so did danger. Quietness could be adaptive. Many modern hunter-gatherer groups modulate speech and movement to match their environment. Soft voices in open terrain, louder ones under canopy. It is not impossible that, under the long twilight of post-Toba skies, human speech itself became quieter, lower, and more deliberate. The idea of a linguistic bottleneck is, of course, speculative. There are no recordings from 70,000 years ago, no written traces of the languages that may have existed, but linguists studying the roots of modern tongues sometimes look for statistical fingerprints of contraction, patterns in phoneme distribution, syntax depth, and semantic range that might suggest a small ancestral population. Some computational models propose that the proto-languages underlying all known human speech could have emerged from a narrow lineage during or after this bottleneck. If true, much of the diversity of sound and structure that defines humanity today could trace back to the survivors of a single storm. The question then becomes, what does silence leave behind? In biological evolution, bottlenecks reduce diversity, but can accelerate adaptation once populations recover. The same may be true for language. When conditions improved and groups reconnected, their isolated tongues would have collided, merged, and reinvented each other. Each meeting between communities would have been a laboratory of hybridization, a reawakening of linguistic creativity. Out of that recombination, the capacity for abstraction, metaphor, and eventually symbolism could have expanded explosively. In that sense, the silence before may have been the soil for the noise after. This dynamic is mirrored in other species. Animal communication systems often contract under stress and expand under stability. When ecological pressures intensify, calls become fewer and simpler, focused on alarm or coordination. When conditions ease, variation returns. Mating calls diversify, songs lengthen, play resumes. If early Homo sapiens experienced similar cognitive pressures, then the post-Toba recovery may have been not only demographic, but also linguistic, a flowering after long compression. To think of humanity as having passed through a quiet age is unsettling, yet oddly comforting. It suggests that silence is not absence, but incubation. Language did not vanish in those years. It waited. It endured in whispered exchanges, in small vocabularies honed for survival. It lived in the hum of work, the rhythm of walking, the murmur of fire tending. What disappeared was not the ability to speak, but the excess, the songs, stories and speculations that flourish only when the world feels safe enough to listen. We can imagine those small communities, a few families gathered in the dusk of the Ice Age, their words sparse, their gestures eloquent. Perhaps they no longer needed names for distant things. Perhaps they spoke more with eyes and hands. In such intimacy, communication becomes minimal but deep. Every word is shared meaning. Every silence is understanding. It may even be that this quiet intimacy shaped the emotional depth of human communication. Modern languages, for all their complexity, retain traces of that closeness. The use of tone, pause and rhythm, the unspoken side of speech, may have been refined in those long, quiet generations. When the world was small, words carried more weight. By the time populations began to grow again around 65,000 years ago, the fragments of those dialects likely met and blended. Some words survived, others vanished. New combinations formed as people migrated, traded, and reunited. Language expanded again, carrying within it the echoes of its silence, the intervals, the rhythms, the restraint that had once been essential. Did crisis quiet our species before it taught us to speak? Perhaps. Or perhaps the quiet was the teaching. The long silence between eruption and recovery might have tuned our ancestors to listen more closely, to one another, to the world, to the patterns of fire and wind. Speech, when it returned in fullness, would then be not a sudden invention but a memory reawakened. In this view, language is not the opposite of silence, but its child. Every word we speak today carries the imprint of the millennia, when saying less meant surviving more. The ashes of Toba may have dimmed the sun, but they also softened the human voice, preparing it for the kind of meaning that requires stillness to be heard. Imagine waking each day into a world that no longer behaves the way it should. The rains that once came on time now skip entire years. The rivers shrink and return without warning. Animals vanish from familiar paths, and the wind carries a cold that bites differently each season. Around 65,000 years ago, humanity stood inside this uncertainty, not yet explorers of the globe, but reluctant students of change. It was an age when survival no longer depended only on strength or memory, but on curiosity itself. The cold had met the curious, and something new began to take shape inside the human mind. The environment of that time was not the stable savanna of our earlier ancestors. The planet was still cooling in the long shadow of volcanic winters and shifting glacial cycles. Dust from deserts drifted across continents. Vegetation zones had contracted into mosaics of grassland, steppe, and dry woodland. Food sources were erratic, and regions that once supported large herds became barren within a generation. To endure such instability required not only endurance, but improvisation. This is where curiosity, that most fragile and dangerous of instincts, became a tool. Archaeologists studying sites in southern and eastern Africa from this period find subtle signs of behavioural flexibility. Stone tools show increasing variation in form and raw material, suggesting that people were experimenting with what worked in different conditions. Some groups shifted to using finer-grained rock types, improving edge retention. Others combined new forms of hafting or resharpening techniques. These changes do not mark a sudden revolution, but a gradual accumulation of insight, the kind of innovation born not from comfort but from necessity. When the landscape became unpredictable, those who could question their own habits may have survived. The same applies to diet. Stable isotope studies on ancient shell middens and animal remains reveal widening food spectra, meaning humans were eating a greater diversity of plants, animals, and marine resources than before. In regions near coasts, foragers turned increasingly towards shellfish and tidal foods. Inland, they scavenged roots, seeds, and small game. Curiosity in this sense was not intellectual but visceral. It was the willingness to taste the unknown, to follow a new trail, to learn which stones sparked better fires or which seeds could be crushed into paste. In an unstable world, experimentation became inheritance. Neuroscientists studying curiosity today describe it as a cognitive drive for uncertainty reduction. The brain releases dopamine when it encounters new information that promises reward or understanding. It is, biologically, a survival mechanism, a way of mapping the unpredictable. In the Pleistocene, this trait would have been a compass through chaos. The curious individual took risks, but also gathered more information. They noticed changing winds, migrating herds, and new water sources. They connected patterns others ignored. In times of abundance, such tendencies may have been unnecessary, but in crisis they became the difference between knowledge and extinction. One of the clearest archaeological signals of this mindset lies in tool repair and reuse. Before, stone flakes were often discarded after short use. Now we see evidence of reworking, edge maintenance, and adaptation. People were conserving resources, yes, but also observing performance, testing the limits of materials and learning from failure. Curiosity had become iterative. Each experiment, each mistake carried forward. Over generations, this accumulation of micro-innovations laid the foundation for later leaps in technology. Fire use also reflects this flexibility. Charcoal layers from sites in Africa, Arabia, and South Asia show irregular but persistent burning, not constant habitation, but repeated return. This suggests that groups were moving seasonally, following patterns of regrowth, game migration, and shelter availability. To thrive under such patterns required memory, communication, and planning. Traits intertwined with curiosity. The mind that could wonder why one valley stayed green while another dried would be the mind that returned to it in time. Curiosity does not flourish in isolation. It depends on cooperation. In small foraging bands, every individual's observation mattered. If one person noticed a new type of stone or an unfamiliar plant, that knowledge had to be shared. Cognitive anthropologists describe this as distributed intelligence, a group-level adaptation where curiosity spreads through conversation and imitation. When every life depends on collective noticing, curiosity becomes social glue. It binds people not by hierarchy, but by exchange. The genetic and archaeological records both suggest that human populations during this period were small but not uniform. Different groups lived in diverse ecologies: coastal, savanna, and highland. Each developed unique adaptations, but the common thread was behavioural versatility. This versatility, the ability to learn quickly and apply knowledge flexibly, may have been the single most important trait honed by this era's cold unpredictability. It was evolution's quiet experiment. Could curiosity be selected for? It appears so. Modern humans differ from other primates not only in intelligence, but in exploratory behaviour. Even infants show an unusual drive to manipulate, observe, and understand. This trait is costly. It leads to risk-taking and inefficiency, but in variable environments it pays off. The late Pleistocene was precisely such an environment. Selection pressures would have favoured individuals who sought novelty, who questioned familiar routes, who combined known tools in new ways. The cold did not just test survival, it trained the mind to anticipate change. In this light, the transition from the late Toba centuries to the early expansions of humanity was not merely demographic, it was psychological. Each encounter with scarcity rewarded adaptability, reinforcing neural pathways for problem-solving and foresight. Over thousands of years, this shaped cognition at the population level. The same flexibility that allowed a band to survive a failed hunt would, much later, allow others to cross continents and invent art, language, and culture. Curiosity was the seed of all of it. What might curiosity have looked like in daily life 60,000 years ago? Perhaps it was a child touching an unfamiliar stone and noticing how it fractured. A hunter following strange tracks instead of familiar ones. A gatherer testing whether seeds softened after being left near the fire. These were not deliberate inventions, but instinctive acts of exploration. Countless small moments of wandering that accumulated into innovation. The first composite tools, the earliest pigments used for practical marking, the beginnings of storage and delayed consumption, all trace back to curiosity applied to scarcity. Even at the genetic level, evidence hints at selection for cognitive endurance during this period. Studies of ancient DNA and population models suggest that certain genes associated with neural plasticity and stress response became more frequent during late Pleistocene bottlenecks. These would have enhanced learning, memory, and risk evaluation, traits that favour exploration in changing environments. The same neurological circuitry that fuels curiosity today, releasing reward for discovery, may have been refined under these ancient hardships. The environment gave little room for complacency. Glacial advances cooled highlands, shifting rainfall belts southward. Regions that had once been rich in vegetation became corridors of dust and wind. Those who stayed had to adapt their technology, shifting from heavy specialized tools to lighter, multi-purpose ones. Archaeological layers from sites like Pinnacle Point, Sibidu Cave and Port Kepik in Africa show precisely this, a move toward versatility and fine control. These innovations were not cultural luxuries. They were behavioral experiments, each answering the question, what still works? Curiosity also altered how humans perceived the unknown. Earlier hominins likely avoided uncertainty as a threat. By this time, our ancestors were beginning to treat it as information. To see a new landscape not as danger but as potential required a cognitive reorientation, an optimism of the mind against the indifference of nature. The cold might have reduced their numbers, but it may also have refined their curiosity into a survival strategy. Those who dared to look beyond the next hill, to ask why one valley stayed warmer or which direction the birds were migrating, became the ancestors of those who eventually left the continent. The shift was subtle yet profound. Exploration became habitual. Curiosity ceased to be optional and became a form of metabolism, something humanity could no longer turn off. In a sense, it was the mind's way of keeping warm. When the environment grew colder, the brain burned hotter. Archaeological traces support this growing cognitive restlessness. Toolkits diversified regionally, suggesting experimentation across ecological gradients. Pigment use expanded for practical, not symbolic purposes, perhaps for hide preservation, or as adhesive components. Hearths appear in new contexts, marking a broader range of environments humans could inhabit. These were signs of a species not retreating from difficulty, but learning to bend around it. If we listen closely, this was the age when humanity began to sound different. Curiosity changed not only what we did, but how we thought. It taught us that problems had hidden layers, that there was something to find in what seemed useless. This mental framework, the belief that the unknown is worth approaching, may be the most enduring legacy of that cold millennium. It was curiosity, not comfort, that made intelligence sustainable. Did curiosity become a survival trait? Everything we know suggests yes, but it wasn't a single mutation or insight. It was the cumulative reward of countless small questions asked in the cold. The same curiosity that once saved us from freezing now drives our search for knowledge, our science, and even our storytelling. In the beginning, it was simply about finding food, warmth, and safety. But in learning to ask why about those things, humanity found the habit of asking why about everything. The cold may have hardened our bodies, but curiosity softened our minds, made them open, elastic, and restless. It made survival a form of thinking, and thinking a form of survival. And when the world finally began to thaw, curiosity was ready to move with it. Imagine waking to a light you almost forgot existed. The air still holds a memory of cold, but it carries something else now. The scent of soil, of water running again, of leaves uncurling after centuries of grey. Around 60,000 years ago, after millennia of dust and drought, the planet began to exhale. The skies cleared, sunlight strengthened, and green crept back across continents that had long been brown. This was the first true rebound after the Age of Ash. Not a return to what once was, but a slow, quiet reawakening. For tens of thousands of years, ecosystems had lived on the edge of survival. Forests had retreated to refuges, rivers had shrunk into trickles, and the wind carried more sand than seed. But climate does not rest. The same orbital rhythms that once deepened the ice now began to shift again. Subtle changes in the tilt of Earth's axis and the shape of its orbit altered how sunlight reached the planet. Summer warmth grew stronger in the north, triggering a chain of feedbacks. Ice sheets paused their advance. Dust in the atmosphere settled. Monsoon systems revived. Across Africa, South Asia, and parts of the Pacific Rim, the long glacial drought began to break. In lake sediments and ocean cores, scientists can trace this awakening as a change in colour. Layers of pale dust give way to darker, organic-rich mud, rich with pollen and plant remains. These tiny grains, preserved underwater for 60 millennia, record the slow return of vegetation. Grass pollen dominates first, followed by shrubs, then trees. The recovery was not uniform. It rippled across the world like a wave following rainfall and temperature. In some regions it took centuries, in others millennia. But by 60,000 years ago, much of the southern hemisphere had begun to bloom again. Southern Africa, where small bands of humans had endured the cold centuries along coasts and refuges, saw the return of inland life. Rivers that had been seasonal began to flow year-round again. Savannas expanded. In places like the Kalahari and the Limpopo Basin, wetlands reappeared where salt flats had been. The soil, enriched by long deposition of dust, supported fresh vegetation. With it came animals, gazelles, zebra and elephants, their migrations reinstating the old cycles of abundance and absence that defined life before the eruption. To human eyes, the change must have felt miraculous. For the first time in many generations, the world looked fertile again. Archaeological sites from this period reflect the rhythm of this renewal. Layers of ash and sterile sand give way to layers rich in charcoal, bone, and tool debris, signs of longer habitation, more frequent return. Hearths reappear in caves that had lain unused for millennia. The diversity of stone tools increases, not through radical innovation, but through continuity. Evidence that groups were staying long enough in one place to refine what they made. Population density, inferred from the number and spread of sites, began to rise again. It was as if the Earth, by softening its grip, had invited humanity to settle and plan. Climate models suggest that rainfall across much of Africa and South Asia increased by as much as 40% during this period compared to the previous millennia. Monsoons strengthened, drawing moisture inland, while cooler northern ice stabilised ocean currents. Even the great dry zones, the Sahara, the Arabian Peninsula, saw intermittent greening. Fossil river systems that had lain dormant reactivated, connecting lakes and wetlands into new corridors of life. The same landscapes that had been impassable deserts now became pathways. The return of green reshaped not only ecology but possibility. Plants themselves were the quiet architects of this transformation. When vegetation returns after long dormancy, it alters everything. It traps dust, stabilizes soil, and influences rain through transpiration. In many regions, trees that recolonize slopes and riverbanks helped lock moisture into the ground, reinforcing their own survival. The more the earth grew green, the easier it was for it to stay that way. The biosphere had entered a positive feedback loop, a reversal of the decay that had followed Toba's ash. This ecological rebound was not simply global, it was patchwork. While Africa and parts of Asia flourished, higher latitudes remained frozen. The cold had not vanished, it had retreated into its familiar strongholds, leaving a band of habitable land stretching across the equator. It was within this band that early Homo sapiens regrouped and multiplied. Genetic models show a slow but steady increase in effective population size after 60,000 years ago, consistent with improving conditions. The long bottleneck was easing. But recovery is not restoration. The environments of this new green world were not the same as before. Forests grew in different places, species composition shifted, and rainfall patterns were altered. Many megafaunal species that had barely survived the cold years failed to return in full. In some cases, extinction had already begun. The ecosystems that emerged were younger, faster, more opportunistic, dominated by generalists rather than specialists. In that sense, the new green was more fragile but also more flexible. Humans, too, reflected this new flexibility. Archaeological evidence from caves and open-air sites shows diversification in resource use. Coastal groups combined marine and terrestrial foods. Inland groups exploited both grassland and woodland ecologies. Such flexibility was only possible in a world that provided enough variety to explore. For the first time in a very long while, risk-taking was again rewarded. The rhythm of survival shifted from endurance to curiosity. The green world encouraged movement, experiment, and contact. This rebirth of ecology also reshaped the emotional relationship between humans and their surroundings. In the cold centuries, survival had required caution and silence. With the return of warmth came the return of abundance, and perhaps of wonder. To see rain after decades of drought must have felt like revelation. The same rivers that had once been grave markers of failed migrations now became living boundaries again. For those who inherited memory through stories and ritual gesture, this transformation may have carried the weight of myth, the earth returning from death. Evidence from sediments at sites such as Lake Malawi, Lake Tana, and the Arabian Lakes confirms that ecosystems in these regions underwent rapid hydrological recovery around this time. The isotopic signatures of carbon in plant remains show a shift from arid adapted vegetation to mixed or humid species. This transition marked the end of what climatologists call 𝐓𝐈𝐌𝐿𝐿 events, intervals of global dust and drought, and the onset of a relatively stable interstadial, a warm pulse within the broader ice age. For the humans living then, it was not the end of hardship, but it was the beginning of rhythm again. Seasons returned, predictability returned. Time itself became trustworthy. Archaeologists sometimes describe this phase as a demographic bloom. Small, isolated groups began reconnecting across regions, exchanging not only genes, but knowledge. Tool styles became more consistent across wider areas, suggesting renewed contact networks. It is here that we begin to glimpse the faint outlines of social rebuilding. Not yet the grand symbolic cultures of later millennia, but the scaffolding of cooperation and continuity. The world was no longer silent. It was murmuring again. The return of vegetation also affected the visibility of humanity. For generations, people had lived in sparse landscapes where footprints vanished in dust and wind. Now, with grasses and mud returning, traces began to persist. Campsites left impressions, fires left black rings in soil rich enough to hold them. In a literal sense, the earth began to remember us again. Even so, this green age was not evenly kind. Fluctuations continued. The ice sheet still advanced and retreated in the north, sending pulses of cold air and shifting rainfall belts. But each pulse was smaller, each drought shorter. Life had found its balance once more, if only for a while. For a species shaped by crisis, this stability may have felt unreal, a fragile miracle sustained by invisible forces. What happens when sunlight feels new again? The answer, perhaps, is gratitude, but also restlessness. As ecosystems recovered and populations grew, curiosity that had once been the key to survival became the spark for exploration. When the first return of green swept across Africa and Asia, it gave humans not only food and safety, but possibility. A wider world awaited, its rivers open, its winds calmer, its horizons clear. For now, humanity stayed within its cradle, watching the earth recover. But the balance between staying and moving was beginning to tilt again. The sunlight that returned after 60,000 years ago did not restore the old world. It created a new one. It was softer, greener, and more inviting, yet still carrying the memory of darkness. The people who walked beneath it had inherited both endurance and imagination. They were the descendants of firelight and famine, now walking under skies that shimmered with renewal. The world had turned a page, and so had they. Imagine this. A clear morning somewhere on Earth, sunlight bright, air still, until it isn't. The ground trembles, birds take flight, and within hours a column of ash climbs higher than any cloud, punching through the tropopause into the stratosphere. Satellites would capture it instantly, and millions would watch it unfold on screens. Within days the sky darkens worldwide. The sun grows pale, planes stop flying, crops begin to fail. It sounds like fiction, yet this is something our planet has done before, many times. The line of ash that geologists still trace through the soils of Asia, Africa and the Indian Ocean is not a warning from myth, but a record of precedent. The Toba eruption 74,000 years ago was one of the greatest natural disruptions in human prehistory, and as far as we can tell, it was not the last of its kind. To understand what such events mean for the future, scientists study the frequency of super-eruptions. those rare volcanic episodes that eject more than 1,000 cubic kilometers of material. The record, scattered across continents and buried under time, reveals that the Earth produces eruptions of this scale roughly every 50 to 100,000 years. The interval is uncertain because each event leaves a different kind of evidence: ash layers, caldera structures, or geochemical traces in marine sediments. But the message is simple enough. Toba was not unique. It was part of a geological rhythm far older than our species. Volcanologists classify eruptions using the Volcanic Explosivity Index, or VEI, a logarithmic scale that increases tenfold with each step. Mount St. Helens in 1980 was a VEI 5, Tambora in 1815, whose ash darkened the world and caused the year without a summer, was a VEI 7. Toba reached VEI 8, an eruption thousands of times larger than anything witnessed by civilization. Such events are beyond imagination. Columns of gas and ash rising 40 kilometers into the air, pyroclastic flows covering tens of thousands of square kilometers, sulfur aerosols encircling the planet. These are not mountain explosions, they are atmospheric engines. Today, scientists can model these dynamics with precision that would have astonished the early geologists. Using satellite data, climate models, and ice core chemistry, they can reconstruct how sulfur particles from large eruptions reflect sunlight and cool the planet. Even a single moderate eruption, like Pinatubo in 1991, caused a measurable global temperature drop of 0.5 degrees Celsius for several years. Scaled up by orders of magnitude, a super-eruption could trigger years or even decades of global dimming. It would not end life, but it would stress it severely, through crop failure, disrupted rainfall, and cooling that could cascade through ecosystems. The question is not if such an eruption will happen again, but when. The geological record points to several candidates for the next source: Yellowstone in North America, Taupo in New Zealand, Aira in Japan, and Campi Flegrei in Italy. Each is a vast caldera system fed by magma chambers kilometers deep. None show signs of imminent activity beyond normal geothermal breathing, yet every one of them has erupted catastrophically in the past. The recurrence interval for Yellowstone-sized events is roughly 600 to 700,000 years. The last occurred about 640,000 years ago. That sounds like timing, but geology doesn't follow calendars. It moves on stress, melt, and chance. Modern volcanology has one advantage over the past: observation. Networks of seismometers, satellite interferometry, and gas sensors now track magma movement with extraordinary sensitivity. If a super-eruption were beginning, we would likely have weeks or months of warning, swelling ground, tremors, and massive gas emissions. Yet detection is not prevention. Humanity could evacuate millions from local zones, but not from global climate effects. The sky, once filled with sulfuric haze, would dim every sunlit hour. Air travel could halt, harvests could decline, and the atmosphere could cool by several degrees. The scale of vulnerability is not biological this time, it is infrastructural. That contrast between ancient survival and modern fragility is what makes the Ashline a lesson. 74,000 years ago, our ancestors endured with almost no technology beyond stone and fire. They adapted because they were mobile, sparse, and patient. Today, we are many, stationary, and dependent on networks. What was once resilience through dispersion has become risk through connection. The same global system that can reroute food and aid across oceans could also amplify the shock of sudden cooling. Modern civilization's strength, integration, is also its exposure. To quantify that risk, scientists have begun modelling super-eruption resilience the way epidemiologists model pandemics. The goal is to estimate how long the atmosphere would remain altered and what that would mean for agriculture, energy, and ecosystems. Recent studies suggest that a Toba-scale eruption would inject hundreds of megatons of sulfur dioxide into the stratosphere, forming aerosols that could reduce global sunlight by up to 10% for several years. Global mean temperature could drop by 3 to 5 degrees Celsius, similar to the cooling of the last glacial maximum. Recovery would take decades. The direct death toll from ash would be small compared to the indirect toll from famine and collapse of trade. But such models also show that humanity is far from helpless. Unlike our ancestors, we can see it coming. We can measure ash plumes, track jet streams, and model their spread in real time. We can stockpile food, develop resistant crops, and maintain seed banks like those hidden beneath Arctic permafrost. These are modern equivalents of refugia, safe places for life to wait out catastrophe. In a strange way, the same impulse that helps small groups survive Toba's chill, preparation, observation, cooperation, remains our best defence today. The geological lessons of Toba also extend beyond fear. When scientists drill deep into the layers of ancient ash, they find not only destruction, but recovery. Within a few thousand years of the eruption, forests regrew on Sumatra, lakes refilled, and ecosystems stabilised. Life, it turns out, is better at healing than predicting. The Earth's own resilience is immense. What collapses are systems of balance, not the planet itself. Recognising this can ground us. The question is not how to avoid change, but how to endure it intelligently. From this perspective, studying prehistoric catastrophes is less about preventing them than about understanding scale. Humans evolved inside cycles of volatility, climate swings, droughts and eruptions, and learned, over millennia, to live with instability. The myth of a stable world is a recent one. The geological record shows a planet that has never truly been calm, only between disruptions. In that sense, Toba is not a warning of exceptional danger, but a reminder of normalcy on deep timescales. Volcanologists sometimes refer to planetary risk baselines, the natural background probability that the Earth will experience an event large enough to affect the global system. For super-eruptions, that baseline is roughly 1 in 10,000 per century. For context, that's higher than the risk of a global asteroid impact of comparable scale. Yet because it operates in geological time, it feels distant, almost abstract. The challenge is psychological, not physical. How to remember the slow threats amid the noise of immediate ones. To study the Ashline is to study humility. Each layer of volcanic glass and tephra in the geological record is a pause mark in the planet's breathing. Moments when Earth reminded life who sets the tempo. Yet within those layers are also traces of adaptation, new species, new soils, and eventually us. Every eruption has reshaped ecosystems, reset evolution, and fertilized oceans with dust that seeds plankton blooms. The ashes that kill are the same minerals that later feed. Even catastrophe participates in continuity. Modern research into volcanic aerosols has unexpectedly influenced climate science itself. The same models that estimate cooling after eruptions are used to project anthropogenic warming. Studying how the planet cooled after Toba or Tambora helps refine our understanding of how sunlight, particles and greenhouse gases interact. In that sense, the ashes of the past are still teaching us how climate behaves. Each eruption becomes both a warning and a laboratory, a natural experiment in planetary physics conducted over deep time. Could another eruption ever shrink us again? Perhaps not in number, but possibly in perspective. A future super-eruption would not erase humanity, but it would remind us of scale. It would shrink the illusion of control, restore proportion to our self-image. The Earth does not conspire against us. It simply continues. Our task is not to dominate it, but to stay aware of its rhythms, to read the ashlines for what they are, signatures of an ongoing indifferent creativity. In the end, the story of Toba is not about extinction, but endurance. The ash that nearly hid us also preserved the evidence of our survival. It became the archive of resilience. To look back at it now, through microscopes and models, is to glimpse our species as part of a much older pattern. Fragile, adaptive, temporary, and astonishingly persistent. We do not stand apart from the planet's cycles. We are one of their outcomes. And perhaps that is the quiet reassurance behind the fear. The Earth has ended worlds before and will again, but it has also kept making new ones. Life, in its stubborn chemistry, finds ways through ash, ice, and dark. We are its latest experiment, still learning to live with the same fire that made us. Imagine the first sunrise after the ash, the air still heavy, the world still grey, and yet there, above the horizon, light. Not bright, not warm, but unmistakably alive. For those who saw it, the survivors of the eruption that nearly silenced our species, that light was not just the return of day. It was proof that time had continued. After years of twilight, the sun must have seemed like a miracle, not divine, but geological. A memory written across the sky, whispering that endurance is sometimes all that life needs to matter. We can only guess what they felt. They had no words for extinction or climate or history, no understanding of what had happened beyond the horizon. But they knew loss. They had seen rivers turn to dust, trees collapse under ash, and animals vanish from paths once certain. And then one morning, they saw light break through again. In that moment, humanity learned something that would stay with it forever, that the world ends often and yet it goes on. Every era since has carried that memory, not in stories perhaps, but in the pulse of how we adapt. Somewhere in the ancient record of our survival is the lesson that nothing is truly stable, that the earth itself breathes in centuries and exhales in extinctions. The survivors of Toba didn't know they had endured a catastrophe of planetary scale, but their descendants, us, still carry the quiet skill they perfected, to keep going when the world grows strange. The ash settled, the air cleared, and green returned. Children were born who would never remember the grey years, but the silence of that time may have shaped how we think, the weight we give to fire, the reverence we feel for light. When the first humans began to keep flame alive inside hearths, perhaps they were not only warming themselves, perhaps they were preserving memory. To guard fire was to make sure that the darkness never lasted that long again. Every ember we light today, every candle, every city glowing through the night, echoes that ancient defiance. We do not worship fire anymore, but we owe it something. It became the mirror through which we watched ourselves survive. Fragile, clever, afraid, and unwilling to surrender. The same light that once pierced a volcanic dusk now burns in satellites orbiting the Earth, in lamps on the ocean floor, in the eyes of telescopes looking farther than the first sunrise ever reached. The memory of fire, in this way, is not about destruction. It is about continuity. Ash does not only bury, it preserves. Under the layers of Toba's fall lie fossilised forests, lakes reborn, and traces of hearths built centuries later. The same minerals that fell from the sky hardened into the soils that fed the next generation. Out of the dust, fertility returned. Even catastrophe, it seems, has its afterlife. When geologists dig into those sediments now, they are not excavating disaster. They are touching resilience. Each layer is a reminder that life has always been recursive, burning, cooling, and re-emerging in forms both familiar and strange. The survivors of that long winter may not have known that they were ancestors. They were simply trying to endure. Yet their endurance became inheritance. Every living human carries the proof that they succeeded. What did they see in that first clear sky? Perhaps they saw colour return, the faintest blue through thinning haze, the first reflection of sun on water. Perhaps they heard sound return, birds that had migrated back, rivers whispering where they had been dry. Perhaps they smelled earth again, wet, living, ready. In that sensory flood, something inside the human mind might have shifted forever. To survive was no longer just to continue breathing, it was to notice. There is a kind of wisdom that only catastrophe can teach, that life is not guaranteed, that everything can vanish, and that what remains afterward is more precious than before. The people who lived through Toba may not have known science, but they knew proportion. They understood smallness, not as weakness, but as truth. They had felt the weight of the planet and found their scale within it. In a sense, every civilization since has been a long conversation with that memory. The pyramids, the cities, the satellites, all expressions of a mind that once saw its own fragility reflected in ash. Our technologies are not only tools of control, they are expressions of remembrance. Each wall we build, each system we design to measure or predict the Earth, carries the quiet anxiety of those who once waited for the sky to clear. And yet, for all our progress, the lesson remains the same. The Earth is not something to win against. It is something to live within. Toba did not destroy humanity, but it humbled it. It taught us that survival is not triumph, but persistence, the long patience of species and stone. When volcanologists and geneticists reconstruct that ancient event today, they are not writing a story of disaster, but one of proportion. Imagine, again, that sunrise. Imagine standing barefoot on cold ground, the air thin, the silence almost holy. You would not have known how many years had passed, or how close extinction had come. You would only have felt warmth return to your skin. That is the feeling the planet gives after every collapse. Not forgiveness, not promise, but renewal. It is the quiet between eras, the pause before growth. Our species carries an odd gift. We remember what we never lived. Deep in our myths, our religions and our sciences lies the pattern of cycles. Fire and flood, fall and renewal. Perhaps these are not inventions but echoes. Perhaps the first stories told beside the first post-Toba hearths were already rehearsing this truth, that endings are the way the world breathes. When modern science maps these ancient disasters, it is doing what those first storytellers did, trying to translate the scale of the planet into something we can understand. Volcanoes and ice ages become metaphors for our own fragility, but also for our continuity. We look at ash not only to know what happened, but to know what it means to last. If you could walk the slopes of Lake Toba today, you would see a mirror where the caldera once tore open. Forests line its edges, villages dot its shore, and people fish where magma once rose. The lake itself is calm, so wide that from the centre you cannot see the other side. The volcano sleeps, but the earth remembers. Every breeze across that water carries the same molecules of carbon and sulphur that once filled the stratosphere. The sky has moved on, but memory never fully leaves. That is what humanity has learned from fire, that memory is not just recall, it is resilience. Every species that survives carries its past within it, whether in DNA or in ritual or in habit. We have built cities over lava, homes in floodplains, and satellites to watch the next storm. Some call that arrogance, maybe it is gratitude, the need to stay close to the forces that made us. The ashline beneath our feet is a kind of scripture, written not in words but in chemistry. It says that we were small, that we nearly vanished, and that somehow we remained. It asks nothing of us but attention, to remember that all stability is borrowed, all sunlight temporary. It is not a threat but an invitation, to live carefully, knowing how easily the air can dim. What did the survivors see in that first sunrise? Maybe they didn't see the sun at all. Maybe they saw themselves for the first time, fragile, finite, but capable of waiting for light. That is the secret of our species, the inheritance from every winter and eruption we've endured. We wait, we adapt, we begin again. The memory of fire is not about fear. It is about belonging to a planet that burns and cools, that forgets and remembers, that makes and unmakes life in equal measure. The ones who survived did not conquer the earth. They learned its tempo. That rhythm still runs through us, in our blood, our breath, our endless need to understand the world that keeps reshaping us. Somewhere, the next sunrise is already preparing to break through another horizon of ash, literal or metaphorical. When it does, we will do what our ancestors did. We will look up, feel its warmth, and start again. Thank you, fellow Sapiens, for wandering this timeline with me, for drifting into deep time, for slowing down and remembering. If this helped you fall asleep, helped you study, or simply helped you step out of the noise for a while, thank you for being here. If you think more people should know this story, you know what to do. Like, subscribe, share it with the Sapiens in your life, and tell me, are you listening before bed, while working, or somewhere in the world I can only imagine? And as always, stay curious, stay calm. I'll see you in the next story.